Hello, everyone hear me?
Yeah, we can hear.
Okay. If anyone has any problem with my voice, just type it here in the chat. Just say it out loud. Okay. So first of all, thank you everyone for hosting me. My name is Mahmoud Dabbous. I work as a system engineer for a rental company here in Egypt. I'm certified from Meyer Sound, Funktion One, VOID, VOID Acoustics, and Quest Audio. Um, Normally, I do live events, corporate events, permanent installations. This is like an example of some of the work that I did. That was a Maroon 5 concert that we did in Egypt. That was a techno show for two artists called Matam. Uh, I love synthesizers. This is my rig. So that's pretty much about me. I would like to start this session. So first of all, no- all of, all of my information, excuse me, is from a couple or three books. It's like this book, Sound System Design, by a guy called Bob McCarthy. It's an amazing book. It's pretty heavy, but it has all the information that you can think of. Another book is called Between the Lines, for a guy called Michael Lawrence. This guy works for Smart, like the company that does the analyzers. It's such an amazing book. He tries to simplify things. So he talks about system design from a practical point of view. Like he says what happens in the field, like a lot of his personal experiences. He doesn't go a lot into theory. He just guidelines what to do in the field. Uh, Void acoustic guides, especially the bass ones. I have information from that here too. Electro voice subwoofer arrays. Uh, Rational acoustics, which is people who make smart. And there is such an amazing podcast called Signal to Noise. They host a lot of great people like mixing engineers from Nirvana, Metallica, system engineers. They have episodes on tips on new for new engineers on what to do, stuff like this. They have a Discord channel that's very active. You can ask whatever question you want, and it helps a lot. I asked the guys a lot of questions in the past months, and they've been very helpful. Okay, so what's your goal as a system engineer? First of all, designing a PA system. You design it, you go to the event, you deploy it, hang it, rig it, make sure it's working. You start tuning, and you make sure that all the systems are operational and not in terms only of PA. You're talking about mixers, stage, like for the microphones, stage boxes, stuff like this. So your goal is to make sure that all the systems are operational, not only the PA system, everything. So, is anyone asking something? That's okay. No worries.
Please go on.
Okay. So we will agree on three things. First of all, and that's the most important rule, systems interact best when they are at equal levels. This is where you want your systems to be. You want matched levels to be able for them to interact properly. Anything with different levels will cause not a lot of issues, but it will cause some variances that we will discuss. Second thing, no technology available whatsoever that can fix a problem caused by a poorly aimed speaker. So I cannot stress this enough. Design phase or understanding what's wrong with your design is the key thing to know what the problem is. So, for example, you see that you have a problem that you do not have enough highs in a part of the venue. If there is no speaker that's being aimed there, that's your problem. So you need always to go back to the design. What's happening? What's causing this? And you need to make sure that your speaker, all of your speakers are pointed where you want them to be. Third, and the most important thing is why. You need to ask yourself this question every time you're about to make a decision. Before every move, you need to ask yourself why I'm doing this. What's the reason behind my decision? Because with live audio, it's filled with uncertainty. Uh, Whatever you read in the books, in real life, it's a bit different. So you have a lot of things that will affect your decisions. For example, the space that you're putting the speakers in, there's obstacles. Sometimes there are some restrictions that, for example, the screen, they want to make the screen more visible, so you need to take the speakers further apart. All of those decisions that he will make, he will affect something. And your target is to manage those sacrifices. And you can only do this by asking yourself why. So when I will put those speakers further apart, what's going to happen? Why am I going to do this? You need to keep constantly asking yourself this question. So we will start with the first basic thing, which is transmission. So I forgot to open up my camera. Hello, everyone. Sorry. So transmission. First things, you need to understand your signal flow. You need to know exactly where the source is, and you need to know after the source, where does this signal flow until it reaches the listeners. Normally, you will have something like this. This is a very basic setup. So you will have an audio source, which is busy. It might be a mixer that's coming from a lot of mics, a DJ mixer, whatever. You have a source. So the audio source goes into some sort of a signal processing. So this will happen as an electronic transmission through an XLR cable, through a digital cable. There is some sort of transmission that happens into your signal processing. You use this signal processing to apply EQs, you apply filters to do whatever you want to do with the signal. After that, it will go into an amplifier because the signal is very low in voltage, like mic line signals and stuff like this. And speakers require a lot of electricity for it to work. So you will need an amplifier to amplify that signal that can go to the speakers. Then there happens the acoustic transmission, and then there's the listener. This is a normal signal flow for any system. We'll start with the basics. I know that all of you guys know this, but it's very important to understand the fundamentals. So this is a typical sine wave playing at a certain frequency. You have a wavelength, which is the point between two peaks or two troughs. Like how long does it take to complete one cycle from any given point? The height of the signal is the amplitude, so how loud it is. The gain of the signal itself, which is translated in live audio to how many volts. So phase, it's the most important thing in what we will say today. Like everything is built on phase, so it's very important to understand the concept of phase. By the end of this section, I'll have you can guys ask me some questions. Please, if you don't understand phase, just let me know. So let's say we'll start a signal. So the sine wave will start from a point, and then it will complete one cycle, then it will repeat that cycle again. So what if we want to identify at which part the signal starts? We need to be able to pinpoint or to talk to each other saying, yeah, it will start from this point. They used angles to do this because one complete cycle is a 360 degree, so it can go back to the origin point. So they came up with an idea to have degrees, which can tell you exactly where the signal will start from. You have your start from 0, you go quarter the way, 90, 80, 270, 360, and then it repeats again. So now you have a lot of audio sources, for example, mics. You have a lot of signals, and they will all combine into your mixer to form one waveform that goes to the speakers. In order to be able to know what's going to happen when you sum some signals, you need to know two things: the level of each signal and the phase. Those are the two main characteristics that will tell you exactly what's going to happen if you start summing those signals. For example, you have here two sine waves, both playing at the same frequency, both starting from the same point, which is 0 degrees. You add them both and you get summation. You got a 6 dB of summation. Why? Because they both started at the same point. You add them, you got your addition. What happens if you delay one of the signal from the other? For example, you phase shifted by 90 degrees. 90 degrees, let's go back to here. So one signal will start from 0, and the other will start from 90 degrees, which is quarter of the wave itself. You get a 3 dB of addition. What if you go on 120? You have no addition, things stay the same. You go on to 180, now you have cancellation. So by a rule of thumb, up to 90, so 0, you have 6 dB of addition. Up to 90 degrees of phase shift, the addition that you get is 3 dB. You will phase shift them 120 degrees, you have no addition, no subtraction, things stay the same. Starting from 120 to 180, you start entering into a cancellation territory. This is very important. Okay, so frequencies combine together. What does that mean? So the 100 hertz will only interact with another 100 hertz. So when you sum to 100 hertz signal, you will either get addition or you will get subtraction. And depending on the phase, that's going to tell you how it's going to happen. But what if you will mix 100 hertz with a 500 hertz signal? You will get a combined response, a mix between both. So you can see that from far away, it looks like a sine wave. But since you added a 500 hertz signal to it, so the 500 hertz signal is now mixed with the original one. When you combine a 100 signal with a 500 hertz, even if they are phase shifted, nothing happens. They stay the same. You will combine different frequencies, so it will be a mix of both. 3 of them now will make sine wave with the 2500 hertz and the 500. So it's a new wave that is a mix of the 3 waves combined together. So how do we see or visualize sound? It's something that you can hear, but you need to have representation for it. You need to have some data so you can analyze what's happening. We'll touch on the RTA analyzers very quickly because this is the session mainly about design, but you need to know briefly what an RTA analyzer is, because some of the diagrams that's coming that will have some information from SMART, and we just need to know what you're saying. So basically, an analyzer is a software that uses a microphone that can analyze the sound that at the mic position. You have two modes for an analyzer. You have a real-time mode, which tells you, okay, now this kind of signal is coming in. In our case, is pink noise, just telling you what the mic is receiving at this current moment without anything else. You have another mode, which is called a transfer function mode. And the transfer function, it works on comparison. So the software has a clean pink noise signal that's uncolored with anything else. And you take a copy of that signal, send it through your speakers. The speakers will send the sound through the room, and then you will be able to intercept that signal with a microphone, and the software will compare between the clean signal and the signal that's received from the mic, and it will tell you exactly what's the difference. So, for example, if you put in, it analyzes the 100 hertz, for example. Let's say that you have some acoustic problem in the room that amplifies the 100 hertz by 2 dB. So the software will show you a bump at the 100 hertz for a 2 dB. So you will know that something happened with the 100 hertz at that location because the clean signal does not have it. And it always consists mainly of two graphs. You have something called a magnitude, which is the frequency response. And as you can see here, I don't know if you can see it properly because of the resolution, but you have your normal 20 to 20K, and it will tell you we have a bump here, you have a dip here, and so on. The upper one is the phase trace. So in the software, every time you go on a frequency, it will tell you the current phase of that frequency at that mic position. So you would know if there any phase shift that happened. And when you compare two different signals from two different speakers, you will know what's the difference in phase between both of them at the same location. And please remember, to be able to understand what's happening at that point in space with the microphone, you need to know the relative level and the relative phase. And that's why analyzers come in handy, so you can know how much of a phase shift that happened between two speakers, for example, at a given location. So far, does anyone have any questions about what I said? Okay. So, phase and EQ relationship. Any change in EQ will always result in a phase change. How does an EQ work? An EQ has a center frequency. It's a frequency that you choose where you will cut or you will add in that region or in that bandwidth. Up top here is the frequency response curve. Bottom here is the phase response curve. All I want you just to know from here that at the center frequency where there was a dip, and those diagrams are like different bandwidth, like this is a very narrow cut, this is a wider cut, this is a wider cut, and so on. A phase shift happened. So if you can see here, there's a phase shift of 60 degrees. So if let's say if the signal started at 0, you applied the EQ, now the phase shift happened to 60 degrees. Anytime you will apply any EQ, a phase shift will happen. This is useful when it comes to the tuning stage. Unfortunately, we won't talk much about the tuning stage, but it's a very important thing to know when you're designing your system, then you're moving to tuning, because they are both related. If you do your design correctly, tuning will just be something very minimal. And if you do your design correctly without bearing in mind what your tuning plan is, it might throw you off on your ultimate goal at the end. So, sorry? So you need to know exactly, or you need to be aware that any change in EQs will always result in a phase shift. This will affect stuff like aligning your speakers, So, for example, aligning speakers is like just applying delay on one speaker so they would virtually start from the same point. So, if you apply your delay first, for example, then you apply an EQ, it messes up the phase relationship that you spend some time on making sure that they match. So normally you would apply an EQ, so you just make sure that it sounds like you want it to sound. Then you take a look on the phase and the delay settings because by that any phase shift would have occurred by applying the EQ. Then you can do your delay, which will stay in place. So speakers run with electricity and huge amount of power that's being caused by an amplifier. So a part of your job will be understanding how electricity works, especially when hooking up your equipment. Unfortunately, we don't have a lot of time to go to talk a lot about electricity and power, but I'll just touch uh, the main things that you need to know about it. And I would really recommend just dig a little more into electricity, just YouTube videos, stuff like this, to be able to understand more about what's going to happen because it's a main part of your job. So it's always perfect to use the water analogy when it comes to explaining electricity. So you have your main values that you need to worry about, or you need to know about, which is voltage, current, which is in amperes, which is measured in amperes, resistance, which is measured in ohm, and power, which is measured in watts. They are all related. So imagine the water in a water hose. The water itself is the is the voltage. It's the energy or the potential energy between two nodes that will provide electricity to your device. How flowy, let's call flowy, this water will flow through the hose. That's the current. Whether you will have a very low current or you will have a high current, and this is the amperes. Like it's called amperes or amps. It's how much voltage you can have flowing in your signal chain. Resistance. So let's say you squeeze the hose itself, it will choke the current, or the it won't allow the current to move freely through your signal chain. So applying more resistance technically would reduce the current, which would reduce the voltage. So can you see how they are all related? So you increase the voltage or you increase the current, you will have more electricity. You increase the resistance, you have less electricity. So they are all related in that matter. And at the end, the what the outcome of the three together working will cause your power, which is measured in watts. So you can see on a lot of speakers, like when you're checking data sheets, this speaker needs 500 watts of power. This is how much power this speaker can push. And you can only achieve that by having proper electricity, which these days you don't need to worry much about because most of the manufacturers just do those calculations for you and they just tell you, you know what, we just need a power source that provides, for example, 10 amperes and 220 volt, and you're good to go. But you need to know those terminologies because sometimes, especially when you're starting to work in the beginning of your career, you won't work like at big companies. You might work at like a medium-sized company or something like this. So they might have some old equipment that still needs some. You need to know exactly what you're looking for in the manual to be able to decide how many speakers that I can operate using a single amplifier. Electricity comes in two types: single phase and three phase. Imagine the electrical box at your house. Okay, so you go into your room, you charge your phone, you're using one socket, you're just one plug. But this is a single phase. You're getting the electricity through two nodes, a positive and a negative, which you can see, for example, on your adapter on your phone, just two nodes. However, the electrical box at your house, the main one, receives electricity through three wires. So think of it as you have, instead of having one line that has all of your electricity, you now have three lines. Uh, so you can use each line separately from the other, so you can distribute your power evenly. So let's say you have one of the phases, it has a problem, you don't lose all of the power for all of your equipment. No, you have another backup. And it has, of course, some more technical advantages, but it's a bit advanced, so we won't go there. But think of the three phase is that you have a backup for your electricity. You can distribute your loads instead of having one cable, like in the left side of the picture. You're having one cable that has all the load on it. No, you have now three sources of electricity that you can distribute your equipment on. To do that in an event setting, you use something called distribution boxes. Basically, it's a giant electrical socket, thing that you put a lot of sockets and plugs in. So you have here the input that's coming from the main electrical line, and it gives you a lot of outputs that then you can use to power up a lot of different equipment around the venue. This is something when you go to work in any company, you will find it looks like this. It has a lot of different shapes and sizes, depending on how big your electricity is, but you will definitely find something like this in any company. So the most important thing when you are looking at electricity or speakers is whether it's an active speaker or it's a passive speaker. An active speaker is a speaker that has the amplifier already in it. Most probably, and the most common type, it's a speaker that you plug in an XLR cable and it works. Why? The amplifier is already inside the box itself. Passive speakers, on the other side, they require an external amplifier. Why would the company choose to design an active speaker or a passive speaker? I would say the main reason is how cost efficient it is. When you have an external amplifier, you can drive several speakers with the same output. So basically, let's say you have one output, you have one speaker hooked to it. Most speakers has a link or a parallel link where you can connect another speaker directly from it. So basically, you have the other speaker driven for free. This would save you a lot of money instead of having an amplifier for each and every speaker. From my point of view, pros and cons, I love active speakers like the ones that we use in Meyer Sound because it's plug and play. Nothing to me can beat plug and play. Passive speakers require modern DSPs. It's called digital signal processor. It's not only an amplifier, like it's a device that has an amplifier in it. You can connect your computer to the amplifier itself. You can apply the EQs, apply the delay, set up the whole session. Like you have how many speakers, like for example, you have 4 speakers on the left, 4 speakers on the right. You will use 2 outputs. Each output will drive 4 speakers. So you start drawing in your system, and you start managing how the system would work through that processor. It's good, it's great, but I've seen a lot of issues that happens unexpectedly from those devices, and I've tried a lot of them. But issues like stuff like, for example, you have a network port that's not working on one of the amplifiers. You cannot communicate with it. That's that. You cannot communicate with the amplifier. For example, you have one output. For example, you discovered that it's not working on the day of the show. Something happens, and you were in your plan, you planned that you will have 4 speakers being operated by that output, and now your plan is thrown out of the window because you have one output that's not working, so you have 4 speakers that's not working. Those are the cons for the DSPs or the amplifiers, the passive speakers, which I see from my point of view. However, it's useful because you can use different, like for example, it's the same amplifier can work with subwoofers, it can work with speakers, it can operate a lot of speakers at the same time. It can come in handy, but I prefer the active ones because they're plug and play. But let's say you work in a company that has a passive speaker brand, like for example, VOID or Acoustics or something like this. You need to be able to understand how many speakers you will drive using a single output. Normally, in the data sheet, I think I have the data sheet here. Okay. Sorry. So normally you would have in the datasheet or the manual, it will tell you, for example, let's imagine an amplifier with one output. Normally, at least you get 2, but for the sake of the argument, let's imagine one output. So in the datasheet, it will tell you, okay, so that amplifier is capable of driving speakers on the 16 ohm, 8 ohms, 4 ohms, and 2 ohms. And at each time you increase the resistance, which we agreed it's called ohms. So every time you add the speaker, that means that you're adding another resistance to the circuit because it's another device that's in your signal flow that has some components that might resist the signal flow for a bit. So normally you can calculate your load by checking your speaker first. So let's say you have a model of a speaker that requires or that will resist the electricity with 16 ohms or 8 ohms. Let's say 8 ohms. And you have an amplifier that can support 8, 4, and 2 ohms. The moment you add another speaker, your load gets cut in half. So if you have one speaker, so you require an amplifier that can handle 8 ohms. You add another speaker that's linked to that speaker, then you need your amplifier to be able to handle 4 ohms. If you'll add 3 speakers, it's somewhere between 4 and 2. If you will add 4 speakers, you will need your amplifier to be able to handle 2 ohm performance. So in here, if you can see this diagram, so if you have a total load, if you have 2 speakers, each one that's 8 ohms, so your total load will be 4. If you have 2 speakers, each one rated 16 ohms, so your total load will be 8 ohms, so on and so forth. So before hooking up a lot of speakers to the same output, you need to check, first of all, what's the resistance on each and every speaker. You need to check the manual, see what kind of resistance does this amplifier handle, and then you do your math. Is this part not clear to everyone? Because this is very important. If you have any questions, please let me know. So we agree that an amplifier is a device that amplifies the signal. What does it amplify? It amplifies the input signal. So you plug in a microphone into an amplifier. The amplifier will take that input signal and it will start making it bigger, louder, more, which means more electricity. You have something called voltage gain, and we will touch on this very quickly. So it's how many times you are amplifying the signal. It's 10x, 20x, 40x. You don't need to know those numbers. This is just to break down what's happening inside an amplifier very quickly. So, for example, if you are amplifying the signal by 10 times, you have a nominal meter, or you have the like normal operating levels, which is your VU meter. You see the meter on the mixer, it stays green, it's okay, yellow, it's like a traffic light. The maximum you can reach is a 1.4 volts of input. This is where you can see that's the green line. Anything above that, it starts going towards distortion more and more. So when you are amplifying the signal at 10x, if you have a 16 ohm load, which is, let's say, one speaker hooked up to the amplifier, you will get a certain amount of power, which is 12.5 watts at 10x multiplication or amplification. Let's say you hooked up two speakers to the same output. So now the power will change. Oh, sorry. Yes, two speakers. You connected here four speakers, so same thing. Power will change. So every time you change the voltage gain, or changing the voltage on your amplifier, depending on the resistance, the power will change. And that's what I don't like about passive speakers, that the performance is not consistent. Every time you have different loads on different amplifiers. So for example, you will have one amplifier that has subwoofers that has different uh, resistance values. You will have another amplifier that's operating the highs. You will have something that's operating something different. With each resistance and each multiplication factor, amplification factor, you will have different power values that you will need to spend some time in the field matching those levels, because systems interact best when they are at equal levels. So you will spend some time just making sure everything is on the same level, because each amplifier will amplify the signal in a different way. What else I want you to take note of in this diagram is that once you start increasing the intensity of the gain on the input signal, the change is not relative to the kind of change that you are doing. For example, you have, let's take a look at the 1.4 volts when you are multiplying it by 40. So at 16 ohms, it's 200 watts. At 8 ohms, they are 400 watts. At 4 ohms, they are 800 watts. At, if you increase the signal to 2 volts, which is increasing the input gain, that's not a double. That's not the double of the volts itself. It's you increase 0.6. But what you get here is doubling in watts. 200, 400, 800, 1600. You go a bit higher and the numbers double again. So anything, that's why going over the nominal operating levels is very dangerous, because any change that happens in the input signal will change the output completely, because you are multiplying it by 40x. So you need to make sure that you are gain staging everything properly. You have nothing in your signal flow that is very high in gain. For example, you have the DJ mixer that's connected to the live mixer that you have, and then is going to the amplifier. You need to make sure that the levels are all constant to make your life easier when you are matching the speakers, because different voltage levels or different input signals will change the outcome a lot in so many different ways, and you want to avoid that. You want to make sure that everything is stable before you start making any tuning decisions or you start making anything on your system. So always stay in the green line, always stay in the green section of the VU meter. It's the best sound quality that you can get out of your system. Connections. You have, when it comes to passive speakers, okay, active speakers, XLRs. Passive speakers, the most common connection is the speak-on connection. you have a two-pole speaker connection, which means that you have only two wires inside the cable, one for the positive side and one for the ground, which is the negative. Or you have a four-pole speaker connection. You have a positive, a negative, and another positive, another negative. That means that you can have two channels, like you can operate a speaker with those terminals and you can operate another with those terminals. Okay, why would you need a two-pole or a four-pole? Why they all don't work with the same kind of connection? It it goes back to the designer, to the manufacturer itself. What you are seeing now is a wiring diagram for a subwoofer in VOID. This subwoofer requires a two-pole speaker connection. By the way, you can use a two-pole speaker connection in a four-pole speaker connection. The thing is going to happen that you will only have two poles that's working because you have only two wires. By looking at this diagram, I can understand that this subwoofer needs only a two-pole speaker cable. How did I know that? So you have your speaker connection. It has +1 and the ground, which is -1. You have +2, -2. If you follow the signal flow, you will find that the +1 is hooked up to one because this is a dual subwoofer box. Like it has two 18-inch drivers inside of them. So the first connection, which is the +1, is hooked up to the speaker. But halfway through, there is a bridge. There's a copy of the same signal that's going to the other driver inside the same box. Same thing happens with the ground part, with the -1 pole. And as you can see, that the two other terminals, they are short-circuited. They're not connected to anything. So by looking at this, I understand, okay, now I need a speak on two-pole connector because the two drivers inside the box itself, they work on one channel. You don't need the other two poles for this. However, you have another subwoofer, for example, at VOID, that uses a four-pole. I want you to disregard this section because this section is for a speakon that's located in the front of the subwoofer. It actually has the same connection, but it's the other way, like from right to left. So we don't want you to confuse yourself with it, but it's the same one as on the one on the left. So we will analyze the speakon connection here. You will find your normal +1, -1, +2, -2. If you follow the signal, so you have the +1 going into a driver, second one going into a second driver. You have a bridge in between, and that bridge is passing the signal to the front speakon that we said that we will ignore, but just telling you that it's the same thing. It's just going to the connector in the front. And you have your +2 and -2. If you follow them, there's a node here. You will find that it's connected to the other driver. So each terminal, so +1, -1, it's connected to the first driver. +2, second 2 is connected to the other driver. So now you understand that you need a four-pole speakon connection because this driver does not pass the signal to the second one. Each one is separated from the other. In the one before it, if you can see, it's the two drivers connected together. In here, each driver is connected to its own terminals. That's how you understand whether you want a normal two-pole or a four-pole, and there's an eight-pole connection, but it's used for it's not very common. It's used for other speakers, but the most common ones are the two poles and the four poles. If you can't find it in the manual, you will find it somewhere in the back of the speaker. You need to find it somewhere, and you will find it in most probably in the manual, but it's very important to know because let's say you plug in a two-pole speaker, two-pole speaker cable in an amplifier and a subwoofer that requires a four-pole. you will only have one driver that's working because the other one has not have electricity in it. So you need to be aware of that so you don't lose half of your power when you are connecting one of your boxes. And this is the most common connection for passive speakers. It's called a speaker. Does everyone understand what I said so far? Anyone have any questions?
Can you just describe the front speaker panel? You didn't explain the rear one. The front one, can you just repeat it again one more time?
Yeah, sure.
Sure.
So I'll tell you
So,
something.
something.
Let me. Can everyone see the picture? The subwoofer picture?
Yeah, we can see.
Okay. On the bottom left here, let me here. You will find two speaker ports. They act exactly or they work exactly as the one in the back. Why they have some of them in the front, we will come to this later when we're talking about subwoofers. But you need to know all about this for now, that you connect them from the front or you connect them to the back, they are both the same connection. Is this clear for now, or do you need me to explain it more?
Clear. It's clear. Thank you.
Yeah, we will come back. We will come to this part exactly why you would need to connect it from the front, but you need to know now that the back is exactly the same as the one in the front. So how do I? I'm trying to remove this circle. Just a moment. Unmute this. Okay. So we touched briefly on the digital signal processors. And what do they do? You have two types of DSPs or digital signal processors because you have two types of speakers. You have a passive speaker and you have an active speaker. So to manage a passive speaker, you will need something, for example, this is called Q5. This is a VOID amplifier. It's they call it a DSP, not an amplifier, because it's not only an amplifier. So this is for the passive VOID speakers. You can access it with a software called Harmonia Plus. You have a lot of softwares that manage DSPs. Most probably each manufacturer has their own software, and sometimes you can find the third-party application that can work with some of them, but it's preferable to use whatever comes from the manufacturer. So for a passive amplifier, sorry, for a passive speaker, you have the VOID Q5, you have an Harmonia Plus, which looks something like this. You just put in the speakers, you have some settings for the EQs, delays, and stuff like this for speaker. In case of an active speaker, you will have, in our case, like in Meyer, for example, we have something called Meyer Galaxy, and it works, it does not amplify the signal, it just manages the signals that you have. So it's as you can see, it's a box. You put in your inputs. It's an XLR inputs. It takes up to 8 inputs, and it outputs 16 channels. So since active speakers will only use XLRs, so for example, you want to send a left and a right to the main speakers, and you want to send a signal to the sub. So you take your inputs, you put it in the into the processor, and the processor, since that it has 16 outputs, you can assign first output with an XLR. It will go to the left speaker. You can assign the second one to the right speaker, the third output to the subwoofer, and then you can start doing your magic here, like EQs as well, levels, stuff like this, to be able to take control of your system because of the tuning that you need to do. the speaker groups that you have, subsystems like delay systems, front fills, stuff like this, which we will all come to later in this document. With cables, the bigger distance you run, the more you might face of a cable loss, for example. Depending on the cable diameter, so speak on cables, you can find like normally people would use at least 4 millimeters. Uh, Smaller, like XLR cables, of course, has smaller diameters. So you have a lot of cables on the market, but the most important thing, you need to know the diameter. It's not something that you calculate, but you need to know about it. You need to know that it's there while taking your decision, especially in permanent installations. But you need to know that the longer cables that you will run, the more signal loss that you will face. For example, the smaller the diameter is, the greater the loss is. So if you have compare between the 2.5 millimeters and the 1.6 millimeters. So if you are running a 30-meter cable of 2.5 millimeter, you will start losing less than 1 dB. 150 meters, you will lose at the end of the cable, you will lose around 2.5 dB, and that's on 4 ohms. The change in resistance will affect the loss in the cable. So the same cable will lose signal differently at 4 ohms, 8 ohms, and 16 ohms. That's why as well I don't like to run a lot long speak on cables. So you need to be careful about how long your cables are. So you don't, for example, have a distance of 20 meters and then you go get a 50-meter cable and then you coil up the 30 meters because you have a very long cable. Try to have cables that's nearly the distance of the speakers where you're hanging, so you would avoid a lot of cable loss. And you need to know, as we mentioned, that it changes with the resistance. So a 1.6 millimeter cable will lose at 150, like for example, the 2.5 millimeter will lose at 150 meters, will lose around 2.5 dB. The 1.6 millimeter will lose 6 dB. And that's on the same resistance. So it's a huge and significant loss. And when you will think of running of cables this long, I would say go with the digital audio. Like if you have something longer than this, go with optical cables, optical fiber cables, or with Ethernet if you are less than 100 meters, because they won't lose signal as much as electricity will be lost in a normal analog cable. Digital audio, which I was just mentioning, it's used for more longer, and it's a solution now that everyone is going to. So, for example, the new Meyer Sound Panther speakers, the sorry.
किए करेंगे या मैं मंगल या पहना गया जना गया
Okay, so you have at least 3 different forms of digital audio. You have something called AES, which is Audio Engineering Society 3. It looks like exactly like an XLR cable. It uses an XLR connector, but the cable itself, it has to be a 110 ohm cable. Like when you go buy the cable online or something like this, you type down AES and you will find that it's already 110. You need just to make sure that you are getting an AES cable, which looks like exactly like an XLR cable. Sometimes you can use a normal XLR cable, but distances will affect the connection, so you need to be careful with that, not to have some dropouts. But if you don't have digital cable, try an XLR one. It works, it works. If it does not work, you need to think of something different. So you have a stereo signal on the same XLR connection, which is the digital audio cable, AES cable. You just most of the processors now and most of the amplifiers, they have this option. You just plug it in from one side, the other, and you have a stereo connection that you can run for long distances. Not too long, but yeah, significantly long than having, for example, 10 XLR cables that you send for huge distances. You can change all of that with just one digital cable, which will make your life easier. You have, secondly, network digital audio, and the most famous thing of them is Dante. Dante is big now. Everyone is using Dante. It's a real lifesaver. So think of it like this: you have a big band that has for at least 10 artists. Each artist has a lot of instruments. So, and you're standing with your mixer 20 or 30 meters away from the stage. Imagine you in the old times, you needed to have a snake or you needed to run connections for each and every instrument, for each and every mic, for the distance of 20 or 30 meters. A lot of things can go wrong. One bad cable, you need to check, for example, if it's running next to electrical cables, so some interference might happen. A lot of issues used to happen. Now you have Dante. You have a stage box right behind the artist. You plug everything into that stage box. You take one cable, Ethernet or an optical cable. You plug it into the stage box. You plug it into your mixer 20 or 30 meters away, and you have your connection, and you can mix whatever you want to do. So that's a real lifesaver. Think of, but instead of using hundreds of cables, you just have one cable that can solve all of everything. The third form, it would be a manufacturer-specific interconnection. So a manufacturer will have their, for example, their amplifier, and they will have their speaker. They have their own software, and they say, you know what, we will have our own network protocol that our system uses, and you can only use it with our brand. Some people have that, but now there's a new thing. It's called AVB Milan. It's a new protocol that everyone is trying to get certification for. It's very accurate. It's very it's high quality, and it's something called time sensitive networking. So the switch or your connection does not send the information unless it's sure 100% that it will be reached in time. So the moment it's unsure that this packet of data will not be reached in time, which might cause a phase issue because it's a timing issue, it won't send the packet, it will send the next one. So AVB Milan is the most stable form of connection. And I was mentioning that the Panther, the new Panther Meyer speaker, it has an AVB card that's built inside each and every box. So now, what we used to do is that from our processor, we used to run something called a multi-core. A multi-core is like a snake, or it's like a cable that has a lot of XLR cables in it. So instead of running a lot of XLR cables, it's only one cable and it has XLR terminals from both sides. So you need to run this multi-core to each tower, and you need to plug them, and you need to line check each and every one. Now, with every speaker, with the new Meyer speaker, they have the XLR option, or they have a direct Ethernet port built inside the speaker. So what you do is that you get a switch, a network switch, you place it on top of the tower, and you connect Ethernet cables to each and every speaker, and you just send one Ethernet cable to that switch. So instead of having a lot of XLR cables, it's again only one Ethernet cable. It goes to the switch on top of the tower, and from that switch, you connect each and every speaker through a network. You give them IP addresses, and you can now do whatever you want with the signal. You can daisy chain another switch for the other tower from that switch. So that means less cables. It will cut the deployment time significantly, because instead of having 3 or 4 guys, 2 of them working on one tower and the 2 of them working on the other, and they need to make sure that all of the cables are working correctly and stuff like this, you have one guy going on top of the tower connecting one switch and then connecting speakers from it, and you're good to go. So it makes life easier. And everyone is switching to digital audio, and this is one of the very important things that modern engineers or up and coming engineers need to know about, because everyone is switching to that. One of the main tools that you have for design is the prediction softwares. And those are softwares that you can use to have an idea of how the sound would be in your venue. You start by designing your system there. It will help you throughout the decisions, and those softwares are accurate. Like, they are decently accurate, not all of them. I've done some field testing and measurements on different, like, I do the design back home, I go on the field, I take measurements, I check whether they match what I had, and I've had good results with Map 3D from Meyer, Sound Vision from VOID Acoustics, Ease Focus. It's accurate. Let's say it's 80% accurate, but it's a third-party software, and just the manufacturers choose whether they put the speaker files on it or not. Not all the speakers are on that software, but it's widely known and a lot of manufacturers use it. Big companies like DMB, L Acoustics, Meyer, those brands, each one has their own software, and they all do the same thing. It's like Ableton or Pro Tools. They're both DAWs, but this does this differently than the other. So choose what you are most probably, depending on the company that you will work with, depending on the speakers they have, you will use the software. But as again, they all revolve around the same concept. Okay, up so far. Does anyone have any questions? Okay. So now we know what's happening until the signal reaches the speaker. You have the amplifier, you have your input. We talked a bit about them. We need to talk about the basics of a design. And to understand the basics of design or understand what's happening, you need to dissect what happens for the sound in a space. Again, you need to ask yourself why before taking any decision, before doing anything in your design or in the field. You need to ask yourself that question, and in order to be able to ask yourself that question, you need to know what is exactly happening between speakers in a physical space, so you can take the the correct decisions to rectify whatever problem that you are facing. So in acoustic transmission, once the sound reaches the speaker, it's affected by something called the inverse square law. You have two examples here. A speaker that does not have a horn. A horn, it's what directs the sound, the speaker horn. So this is a speaker without a horn, which is normally is a subwoofer. And this is a speaker with a horn that directs the sound. So let's say you take a measurement from 1 meter. Let's say it says 135 dBs. When you double that distance, when you go and take another measurement from 2 meters, what happens is that the signal will decrease 6 dB SPL. When you double that 2 meters, so you go to 4 meters, another 6 dB is lost. You double that, another 6 dB, so on and so forth. So this is the main thing when it comes to understanding the inverse square law. So moving away from a speaker will cause loss in distance, loss in level. You don't need to calculate the loss that you will have. In an advanced course, you will need to understand more how to do it, but for basic design, just stick to the prediction software. Put a speaker on the software, just see where it loses signal, and you will understand it visually. Don't confuse yourself with the math. You don't need to do it on the basic stuff. You will need to do it when you're doing big venues like 10,000 attendees stuff and stuff like this. But for now, stick to the prediction software. It should give you a very good representation of what's happening. So what's your ultimate goal as a system designer and how to achieve it? The ultimate goal is very simple. You have a dance floor or you have a place where people attending a ceremony or a corporate event. There is a space, and this space, you need to fill it with sound. People needs to listen what's happening, so you need to fill that space with speakers to be able to cover it. How to achieve this? You can achieve this with coverage patterns. What is a coverage pattern? The coverage pattern is a geometrical shape that the speaker directs the sound to. So you have a space, let's say it's a square, and you have different speakers with different shapes that will fill up different parts of the room. You need to make sure that the area is covered by choosing the right speakers and choosing the right coverage pattern to end up at the end with coverage all over the listening area. Of course, it's easier said than done, but hopefully by the end of this session, you'll be able to understand a bit what's going on in the room so you can achieve that goal. The second goal that you want to achieve, something called minimum variance. What is minimum variance? That each and every listener will have nearly the same sonic experience regardless of where they're standing in the room. So the only thing that will differ is the drop in level from the beginning of the venue, the first part of the venue towards the back. But still, you need to make sure that the level is uniform, that you are losing level gradually. Like for example, you don't have that you have a high SPL zone at the front of the venue, then you have for some reason a gap in between, and then you have a decent volume towards the back. This is not uniform. This is not gradual. There is a gap in the middle. As your goal as a system designer, you want to eliminate this. You want to make sure that at every location, the frequency response is nearly the same, the level response is nearly the same. So everyone would have a nearly uniform experience of whatever show that you are designing the system for. It's an impossible goal. Like you can never reach perfection with it because there's a lot of things that will affect your decisions, like mainly the room itself, the physics of the acoustics of the place. Might have obstacles. You might have a lot of restrictions. Like normally the fight that you will have is with the light and the visuals guys. They don't want any speakers in front of their precious screens. This will, and sometimes the event promoter will prefer to go with the visuals option. Sometimes events will prefer to make sure that the sound is better. So it's always a give and take, and you need just to be flexible on it because you want to get hired. You don't want to be that uptight person that causes problems. So as long as you know what's happening and you say, okay, you want to take those speakers apart, this will happen, that will happen. Are you guys okay with it? You're okay with it? You go on with the show. Be, don't, you don't need to, your opinion to be the dominant one all the time. Sometimes you'll have to make some compromises. You need to be the person that everyone says, see, Mahmoud is here, the day is saved. Instead of being the person that Mahmoud is here, like it will get super complicated. He won't accept anything, and he will cause us a lot of problems. So you need to make sure that you understand what's happening with the coverage pattern. So when you are faced with that kind of decision, you need to visualize, what's the worst that's going to happen? So yes, I take the speakers apart. What's going to happen here? What's going to happen there? Is there another way that I can solve this problem with? The only reason or the only way that you're going to answer those questions by understanding exactly what your design will cause. So speakers have a coverage pattern. How do the manufacturers decide what the coverage pattern is? A coverage pattern of a speaker, it's the point where this off axis where the speaker loses 6 dB of energy. So if you have at this point, at this measuring point, if it's 0 dB, they would check where the speaker lost 6 dB on both sides, and then they will draw a triangle, and that's the coverage angle of that speaker. So when you read on the data sheet that this speaker is a 90-degree coverage angle, that means that it covers to the side 45 degrees and to the other side 45 degrees. So you add them both, it's a 90-degree speaker. But this is misleading because depending on the frequency, you will have a different wavelength. So lower frequencies have huge wavelength. Higher frequencies have shorter wavelength. So low frequencies tend to travel everywhere. So they are not directional. You cannot control them easily. While high frequencies are easier to control, easier to direct using waveguides, using the horns on the speaker itself. So to describe one speaker with one coverage pattern, this is a bit misleading because the more you go towards the low frequencies, they tend to behave differently. The more you go towards higher frequencies, they tend to be more directional. Like, for example, here, if you are looking at the 10 kilohertz response for an 80-degree speaker, this is a 100 degree, this is a 120, which is very wide. You have 7 degree, which is 3.5 to the right, 3.5 to the left. You have 12 degrees, you have 20 degrees, and this is for the 10 kilohertz response. Let's take a look on some of the coverage angles with the lower frequency in the spectrum. So for example, if you have a 100 degree, sorry, you have a speaker with a 100 coverage pattern of 100 degrees, at the 10 kilohertz, yes, you have your 100 degrees. And as you can see here, you have no sound as it dark blue. But let's take a look on the 1 kilohertz frequency. Now, it's spreading more out. Like you can see here some dips, you can see here some places where they will sum, but with the 100 hertz, it travels more, it travels wider, it's more it's less directional. Let's take on the same coverage pattern with the 100 hertz. It's completely omnidirectional, 360 degrees all around. So what you understand from this is that a coverage pattern, a decent manufacturer will show you diagrams on nearly each group of frequencies, each bandwidth. Like for example, it will tell you, yeah, it behaves at the 10K this way, it behaves on the 1 kilohertz this way, at 100 hertz this way. And this is why is this important? It's important because of how the signal or how the sound will interact in the room. So for example, if you don't know about this information, you say, oh, you know what, it's a 100 speaker, or for example, let's in this case the 20-degree speaker. So the 20-degree speaker, you say, you know what, I can put the speaker here, I can put another speaker here, they are both isolated, this one won't interfere with the second with this speaker and nothing will happen. Completely wrong. Yes, not completely wrong, halfway wrong. So in the highs, yes, they are isolated, but lows will tell a different story, and we will check that in the upcoming slides. But you need to understand that what happens in the lower domain of the frequency is different than what happens in the higher domain of frequency. And this is your main goal of as a system designer, to be able to harness the power of the lows, and you need to harness the isolation power of the highs. So you need to understand how to use the directional part of things when it comes to the higher frequencies to your benefit, and you need to understand what happens with the lower frequencies to your benefit as well, so you can have a uniform response. How to achieve this? You need to understand what summation is. So at the beginning of the session, we talked about summing analog signals. So it's a signal, you sum it with another analog signal, it gives you a response. How is this response calculated? Again, two most important things: relative level and relative phase. You need to know the level at this point in space where you're standing. Let's say you're comparing what's going to happen between two speakers. You need to check this speaker alone. You need to check the other speaker alone, so you know what's the difference in level. And then you need to check what's the difference in phase. And depending on those two values, you will have your answer. I was talking about relative level. Let's dig a bit deeper into that. What is the effect of relative level? At the beginning of the session, I mentioned systems interact best when they are at equal level. Where is that coming from? So if you get two signals, you have here three graphs. You have black one, you have the green one, and you have the blue one. Black one is signal number one, green one is signal number two, and the blue one is the outcome or the summation that's going to happen at this point between the two signals. Signal number one is plotted in a way where it keeps decreasing in level from the other signal, and we will graph out or monitor what's going to happen every time you lower the signal by 1 dB.
Mahmoud, one small question.
Sure.
You told the previous slide you need to have a uniform sound throughout the arena. So
Yes.
if we use different types of brands, now we'll say Meyer and Meyer speakers and acoustic speakers,
Okay.
will we get the kind of uniform sound which you were talking before? Can we get the same?
Yes. By doing this, I'll talk about this very quickly, just to answer your question. At the end, you ask a question. You have two speakers with two different responses. You need to see what's happening, right? This is where your analyzer comes in place. So you put the speaker, you put the microphone 1 meter away, you check the response, you see the frequency response of that speaker. Then you go to the other speaker, you check the response of that speaker, and you put the two traces on top of each other in smart. And for example, let's say that the L acoustic speakers has a boost in the highs. If you manage using EQ to line up the both frequency responses of the speaker to be nearly the same, now you have two speakers that sound the same. Because at the end of the day, what does the speaker do? You put in 100 hertz and it will spit out that 100 hertz. How much is going to split it? Is it going to increase it 1 dB, or it's lower 1 dB or higher? So you will use an EQ to match the frequency response of the speaker. So you would have a uniform response through different brands. Do you understand that, or do you want me to explain it more?
Understood. Thank you. Thank you.
You're welcome. We will touch on that as well, like in the end, but this is purely tuning stuff, not designing stuff. But the designing applies for everything. But the question you asked, it's something that you might face a lot. I face it a lot throughout my work, and it always comes down to matching the frequency of those speakers, just making sure they sound the same. So relative level. What is relative level? It's comparing at a single point what's the difference between the level in that signal and the other signal. So their phase, let's assume here that both signals have the same phase, 0 degree. They're starting at the same point, which we agreed on. It's maximum summation, 6 dB of summation. If they are both matched in level, how do we check that? So signal number 1 is at here 0 dB. Signal number 2 is at 0 dB. They both start at the same phase, have same phase value. The outcome is a 6 dB of summation. Let's say signal number 2 stays the same, but signal number 1 is 1 dB less than the other signal. You will start getting summation, but not the 6 dB summation. If the difference between both of them is 2 dB, you will have summation, but you won't have a lot of summation, and so on. So when you increase the difference in dB or difference in level between two phase matched signal, you will start getting addition. But as one of the signals drops lower in level, the addition does not become as significant as it is when it was in higher level. So let's see the two exact opposites. So you see one signal that at one point they are both matched in level, so you get a 6 dB of summation. And in that case, when one of them is 20 dBs lower, you get around 1 dB of summation, 0.9. So you can see how much level can affect your summation with two signals when they are both at 0 phase. And there's no phase shift between both of them. So, and what does relative level mean is that, for example, if this is 40 dBs, this has to be 40 or 39 or 38. This is the difference between them. It doesn't matter how loud the signal is. What you are caring about is the relative level, the difference between the two signals. This will define how much potential summation you will get or potential cancellation you will get. What will dictate that is the second step, which is the phase. So you need to ask yourself the question. So are they in equal level? Yes, they're in equal level. Okay, so I might get a maximum summation or a maximum cancellation. Which one of them am I getting? You check the phase, and then according to the phase difference between them, you will have your answer. So this is the relative level. Now we move to the relative phases. We mentioned this before, but this is in a different diagram, but it's the same thing that we said before, that if you have a 0 degree phase shift, you can get up to 6 dB. If you have up to 90 degrees phase shift, from 60 to 90 degrees, you will have 3 dB summation. If it's 120 phase shift, no summation, no addition, things stay the same. 150 degree phase shift, you have a negative 6 dB of cancellation, 180 complete cancellation. So again, because this is very important, relative level, relative phase. You want to analyze what's going to happen at a point in the room or between two analog signals, you need to ask yourself those two questions. What is the relative phase at this point? What is the relative phase at this point? And this will tell you exactly whether you will lose or you will have some addition in your signal. Is this clear to everyone? Because this is very important. Any questions? Okay. So we need to just identify or put some labels to that behavior. So you have 5 labels that we can use: coupling zone, combing zone, cancellation zone, combination zone, and isolation zone. Okay? So you have 2 traces. You have a trace if the signal or the 2 signals are 0 and there's no phase shift. And you have 2 signals if there is a phase shift of 180 degrees. So the green line is no phase shift, blue line is 180 degrees out of phase with the other signal. So, and this on the bottom side of the graph, this is the level offset, which is the relative level, how much of a difference in level between the two signals. And on the left side, you have the level change. So let's analyze first if both have no phase shift. Both are phase locked, zero phase shift. So if there is no dB difference, like both are on the same level as we saw before, you will get a 6 dB of addition. From 0 to 6, it's called the coupling zone. It's the zone where both will add together. There is no cancellation. This is where you want to be. The more phase locked the signals are and the more matched in level, this is where you can gain the most out of this relationship between the two signals. If you start moving or decreasing a level of a signal than the other up to 4 dB, so you have here the first checkpoint is at 4 dB. So from 0 to 4 dB difference, you can get up to 6 dB of addition. Starting from the first checkpoint, a 4 dB in difference up to 10 dB in difference, this is where things are either rewarding but not so much rewarding. But if it's not rewarding, it won't hurt you a lot. So why is that? Because first of all, the level difference is increasing. So as we saw here, the more level distance, sorry, the more level difference, the more it will affect the summation process between the two signals. So in here, starting from a difference of 4 dB up to 10 dB, if the two signals are phase locked, you can get up to 3 dB addition. And if they are not phase locked, you can get up to negative 3 dB cancellation. It's not the worst thing compared to the cancellation zone, for example, that we will talk about in a bit. But this is a medium territory. It can be managed. If you cannot manage it, it's not the end of the world. You're not losing a lot of signal. Once you reach a 10 dB of difference, you enter something called an isolation zone, where you don't get a lot of addition if they are phase locked, and you don't get a lot of cancellation if they're not phase locked. It's a place where there is a minimum effect that's happening on two signals, whether they are phase locked or out of phase. What dictate that? It's the level difference. It's very important. Once you reach a 10 dB of level difference, you enter that isolation zone, and this is what normally you are trying to reach when you have two speakers interacting with each other, to maximize your isolation zone as much as possible, and we will discuss how to do this in the upcoming slides. Okay, so let's talk about the combing zone. It's you know what a comb does everyone know what a comb filter is? Just make sure so a comb filter is, sometimes people use it as an effect, but what actually happens is that you have a signal that's interacting with the other, but it's canceling in parts of it and it's adding in the other parts, so it creates those teeth like a comb, hence the term comb filtering. So this is one of the it's a very bad scenario when it comes to system design, because you have one frequency that's very visible that you can hear it, and the other one that's completely destroyed, it's completely cancelled. So it creates a lot of spectral changes, a lot of change in the content of the whatever source that you're playing. For example, if you're playing an instrument, it will add a lot of coloration to it, and like you want to avoid that as much as possible. So when you are in the 4 dB difference and you have the combing zone that's happening because of a time difference in level, this is where you want to avoid. You can start using some methods and techniques that we will discuss on how to try and get out of this combing zone, but it is something that will happen, and I will show you why, but you need to manage how much it's going to happen and the area affected with it. And there are some tricky ways to place them in places where people won't listen. Like, for example, if you have a stadium, so between each and every cluster of chairs, you have like you have the stairs. If you can point this combing that will happen, for example, because this is where you can hang the speaker, if you can direct it to fall onto that line of stairs, no one is there, so it's okay. So this is how you start managing combing zones, and we will talk about that in a bit. The worst case, that the scenario is the cancellation zone. Cancellation zone is when they are both out of phase 180 degrees. You will enter this zone as long as you have 4 or more, the maximum that you have of a level difference is 4 dB. Anything under 4 dB will send you to the cancellation zone. Anything more than the 4 dB of difference, you will start getting into combination zone again, which you won't have a total cancellation. Anything over 10 dB of difference, you enter an isolation zone, which is a safe zone to operate in. Okay, so how to decide which zone are you in? You need to use something called triangulation. This is not something that you will use in small designs, but it's a good way to represent your position in the room and how the speakers will interact with it. So you have your 4 basic geometry triangles. The isosceles, where both all the sides are equal, the angles are equal, you're standing in the middle. You have your right angle, you have your obtuse, where the angle here is bigger than 90. You have an acute is between 90 and between the isosceles triangle. So depending, if you want to analyze what's going to happen in a room, you need 3 pieces of information. You need to know where speaker 1 is, you need to know where speaker 2 is, and you need to know where the listening position is. And according to this, you will have a triangle that will tell you exactly which location are you in, or which kind of zone are you in. Are you in a coupling zone? Are you in a combing zone? Are you in an isolation zone? We will illustrate them with triangles and the colors, and we will see this diagram now. But you need to know exactly which triangle you are in. For example, let's take the isosceles triangle, or a coupling zone. So imagine you have speaker A, you have speaker B, you have listening position 1. So again, what affects the summation? It's relative phase and its relative time. Sorry, relative phase and relative level. So the phase is time, level is level itself. So you need to understand what's going to happen for the sound until it reaches this listening position. If you analyze C1, you will find that you are in an isosceles triangle. You are dead center in the middle. What does that mean? It means that the distance from speaker A to the listening position is equal to the distance from speaker B to the listening position. What does that tell us? If you check, first of all, the relative phase, relative level, you will find that according to the inverse square law, you are away from speaker A the same distance from speaker B, so the level loss will be the same. So if you start with 140 dBs here, and let's say it reaches this point, it's 130 dBs, it's the same distance for the speaker, for the other speaker. So at the end, it's 130 dBs for A, 130 dBs for B, so there is no level difference between them. So now you are in a region where you can have maximum addition or maximum subtraction because you have no level difference. So what's the other thing that will affect our decision is the timing, the phase. So now you need to check what's happening in regards of the time when it comes to this listening position. Here, because it's an isosceles triangle, so the time taken from this speaker to the position is equal to the same time that it will take from this speaker to the listening position, which is phase locked because there is no difference time, so there is no phase shift. So now you are in the summation zone, the coupling zone, and it's symbolized throughout the diagrams coming with this. Like, this is a frequency response. You have nothing that's rolling off. You have complete summation. Same applies if you move backward towards the venue. Again, same distance, same time, you will get the same response. It's a coupling zone. Same thing with the C3. If you have different displacements, like in this diagram, it's different displacements. So A1 with B1, A2 with B2, A3 with B3, and so on. So if you're standing in here, listening position C, if you check speaker A, same distance, B2, distance, same things, no difference in level, no difference in time. So you will have, at this point, it will always be a summation between the speakers, between the two speakers that you are analyzing. Your second triangle is the right angle triangle. And this is the worst thing that can happen to you, because you have a lot of spectral changes because of what's happening between the speakers. So let's say you have speaker A, speaker B, you're standing in here. Distance to speaker A is shorter than distance from listening position to speaker B. Shorter means that the level, so this will travel longer, so the level will decrease more than this, so you will have a difference in level and you will have a difference in time. Depending on both of them, as we agreed before, will dictate what kind of response will happen at that position. So if you take a look at C1, you are closer to A, but very far from B. Like, this is way longer than this side. You will have a combing filter across all the frequencies from the low to the high. You need to know that a phase, in order to affect a low frequency, you need to have a huge phase shift, because, for example, you have you have frequencies that have a wavelength of 3 meters and 4 meters. So in order to be able to phase shift a 90 degrees in a low frequency, you need to move a bigger distance than having to do a phase shift, for example, a 10K, which needs very small distance, like millimeters and stuff like this. While in with low frequencies, you have to walk in half a meter or a full meter to be able to do any change in the summation significantly to any of the low frequencies. So going back to the listening position C1, since that the change is big, because this side, or the sound would travel or a longer distance to the listening position than from A, so you will have a combing across all frequencies. When it comes to point C, so things are starting to even out a bit. Why? Because instead of going very close to speaker A, now at this position, you are far away from A, and B is nearly coming to the same distance, but of course there's still a difference here. But as you can see, it's starting to even out the distance between the listening position 2 and the second speaker. And as you can see here, you will have the combing filter only in the high frequencies, mid frequencies, and the low frequencies will not be affected, because now the time difference is not as big as the C1 here, because here you're very close to the speaker. With C3, as you stretch out the distance between the speaker A and the listening position C, and as you can see here for the third side of the triangle, it's coming closer and closer to be the same distance with A. So the only affected part here is the high frequencies, because the time difference is not as big, so it will only affect the highs, but while in the mids and the lows, you will have things that will stay the same. So depending on where you are standing from the speakers, it will affect the response that will happen in the room. So what do you deduct from this? What we deduct from this is that the displacement between the speakers will affect how much they will interact. As you can see here, you have A, this is the first speaker, and how it will interact with 3 speakers. So you have A, and you have a listening position C, and you have the first speaker, which is displaced greatly. You have a lot of displacement. So the time it will take to travel from speaker B1 to C is huge, which will cause a lot of phase shift. And you can see it here, the relationship from A with B1, since that the displacement is huge, it caused a lot of comb filtering. B is a bit closer. So you can see that the comb filtering is happening from the mid section towards the high frequencies, but the lows is now unaffected compared to the B1 speaker. Why did that happen? Because you got closer to the first speaker. The more you decrease the displacement between them, the more, the less the difference will be in level and in time. How to check with that? Check the closest speaker, which is the B3. You have good relationship up until the highs, and since that the highs is affected by the changes more than the lows, and the speakers are somehow next to each other, so you have only the highs that got affected with this comb filtering. And this is your right angle triangle. Like, you see where you're standing, you form a triangle, and it will tell you exactly which zone are you in. You have the combing zone, which works a bit like the right angle triangle, because it's only a matter of time before you get into the right angle triangle. It's like small range of angles between them. Same thing will happen. You have a C1 location. Since that the distance here is greater than this side, comb filtering all over, you move and you start evening the triangle out. You start getting comb filtering only in the highs. In here, it's nearly towards the isosceles triangle. So you have only minimum, sorry, you have the combing filter happening in the highest frequency and not in the lows or the mids. Same thing here as the one before. So you have the A speaker compared to the B1, since that they are displaced, greatly displaced from each other. A lot of a lot of comb filtering across the frequency range. B2, lows are okay, mids and highs are affected. You move the speaker towards the main one, you get minimum comb filtering because the distance now is nearly the same, and you're not losing a lot of phase shift or level difference. You have your obtuse triangle, which is the isolation zone. And the isolation zone mainly happens, as we mentioned before, you have a speaker that's the coverage pattern is directional more at the highs, and at the lows, it's not that directional, it's an omnidirectional. So once you start going off axis from, like, you have a speaker here, I have another speaker, let me show. So you have the speaker, you have the other speaker, and if you are standing, let's say this one has a coverage angle of this one has a coverage angle like this, So when you're standing here, you are already going towards, you're going away from the coverage angle of the first speaker. Like imagine the distance or the level that will travel from this speaker to that position. It would definitely be a difference more than 10 dB because you are already going out of range from the original speaker. So this speaker will not be effective in summation when it comes to the high frequencies, but since that the lower frequencies are bigger and it travels longer, so you might have interaction in the lower part of the spectrum. How to check that? Here you have the just a moment. So here, if you check listening position 1, the highs are isolated. Here, there's no combing that's happening. You have a lot of combing that's happening here and lows. The more you go through the venue, the combing is not as aggressive as what's happening here at listening position 1, but it's still happening. At C3, at listening position 3, you are already very far away from this speaker, and you are nearly going out of the coverage pattern of the original one. So you don't have a lot of changes. You don't have a comb filter. You have just some spectral change that can be rectified with an EQ or just positioning the speaker properly, but you don't have anything that's affecting your signal. Same thing here as the previous diagrams. This is the main speaker. You have the other speaker, how it's gonna interact with it. It's isolated in the highs. Since that they are greatly displaced, it will affect the lows more. Second speaker is a bit closer, isolation in the highs, a bit of filtering that's happening in the lows. And since that both speakers here are next to each other, so you don't have a lot of time difference when it comes to the lows, so you don't have a lot of filtering that's happening, and you have isolation in the highs. Okay, so guys, would you like to take like a 5-minute break just to drink something, whoever wants to do anything, and then come back, or do you want to continue? What do you guys prefer?
2 minutes break.
Yeah, okay, I know it's a lot. I know it's a lot to digest. So after the break, we'll have a 5-minute question round. So think of what we just said in those 5 minutes. Come up with some questions, and I'm ready to answer them. Okay. So now let's meet. I don't know what's the time there in Sri Lanka, but it's 2 and 8 minutes here. So 5 minutes, and we'll be back. Okay. Is everyone back from their break? Is anyone here?
Yeah, we are here.
Okay, so we have questions. If anyone have any questions, please ask me. I'd be glad to answer them. Because I know this part is a bit heavy, and it might be a bit confusing, but it's very important. Any questions, guys? Okay. So how do we apply those concepts or those triangulation things? How does it happen in the room? How can you see them? There's a progression that will always happen as you move horizontally across a venue. You will face first the isosceles triangle because you will be standing in the middle. Then you will start moving aside. You will getting into the acute. Sure. We have a question here. The question is, can you explain how the comp filtering going to affect on the signal when it occurs? Excuse me. So yeah, definitely. Let's go get a picture of the of a comp filtering. Imagine this. You have a signal, you have an instrument that's playing, and at specific frequencies, you won't have those frequencies. So for example, you have a bass guitar, you have a bassist, okay? So each note is a specific frequency. Imagine he's playing a note that has a frequency that's been cancelled or it's in a comp filtering. You won't hear that note. Same thing applies to the rest of the frequency spectrum. So some notes would not be heard. Some frequencies are not there. Some of them are amplified. So a piano might not sound completely like a piano, or a bass guitar might not sound like a bass guitar. Some of the notes are not there. You can't hear them because they are technically being cancelled. If you want to know more about comb filtering and how it sounds, open any DAW. I am sure you can find there are comb filtering effects, because it does a certain effect that you can use in sound design, but you don't want that when you are playing an instrument that has a specific sound, but you can use it as a sound design tool. But in our case, it's not something that you use for designing, or it's something for effects. It's something that you want to avoid, because as we mentioned now, there are notes that cannot be heard. So you might have a great guitar lead line, some of the notes are not there. So what's the point? Did that answer your question, or do you want me to explain more? Okay. So glad to help. So as you move horizontally in a venue, as we mentioned, you will encounter the triangle progression, the triangulation progression that we just talked about. As we mentioned here, you have the isosceles triangle, then you will go to the acute, then you will move to the right angle triangle, then you will start going to the obtuse triangle, which is isolation. And you can see here that you will have the first one, which is a coupling, you have combing, you have combining something, and comb filtering is something. Combining, they will combine, but they will affect each other at different parts. So you have your coupling, you have your combining, you have your comb filtering, and then you will move into isolation. This is an example of 100 hertz. But why can't you see any cancellation that's happening here? Because the speakers are pretty much close to each other. So the low frequencies, which is towards the 100 hertz, are interacting together in a constructive way, because the difference between speakers and the difference in distance between speakers is not greater than the wavelength of the 100 hertz. So you are still within the acceptable range of a phase shift. The more you start taking the speaker away, the more interaction will happen, as we will see in the upcoming slides. So that was an example of the 100 hertz. This is an example of the 1 kilohertz. Same distance, but a shorter wavelength. So a 100 kilohertz have a smaller wavelength than the 100 hertz. So any change in distance will affect or shift the phase in a greater manner than it will affect the 100 hertz. And you can see that on the diagram here. So here is your isosceles triangle. You can find a lobe here that's not affected. Then you start going into combining and combing and cancellation. As you can see here, there is a blue line which indicates cancellation. Then you start getting again into combining, and then you start getting in isolation. As you can see here, the blue line extends nearly very deep towards the speakers, while the blue line here stops at this part because you are entering isolation. Now the speakers are not interacting with each other. If you see the difference between, sorry?
Mahmoud, sir, actually, I think the screen got freezed a little bit.
Oh, no, thank you very much. Again, so I'll repeat very quickly what happened. So now, moving horizontally, you will encounter the progression of the triangles that we were talking about. In the middle is the isosceles. Here, you start getting into acute and the right angle triangle, which is the red one. And then you start going into isolation. Nothing is affected here because it's a 100 hertz frequency. So the 100 hertz frequency has a bigger wavelength. And since that the speakers are a bit close to each other, you will interact with them in a constructive way. The moment you start displacing them apart more, this is where the lower frequencies will start getting affected. Check the 100 the 1 kilohertz, the 1K. Since that it has a shorter wavelength, so any change so this displacement will affect the summation in zones of the room, some zones of the room. Which zone? Depending on the triangle that you are standing in. So in here, and when you are standing in an isosceles position, you have summation. For once you start going into the right angle triangle, you start having cancellation, and as you can see, the cancellation is going very deep inside the speaker. You start moving towards combining, so you have some cancellation that's happening here, but it's not as aggressive as the right angle triangle. Why is this different? Let's go back over the two things that you need to ask yourself: relative level, relative phase. So here you are going more towards the left speaker, so the relative, and away from the other one. So the relative phase, or the difference in the relative level, a difference in level, is getting bigger, it's increasing. And we agreed on the more difference you will have in level, once you start going past the 4 dB difference, the cancellation or the addition is not as significant. The once you go on more than 10 dB of level difference, you get minimum addition or subtraction. And it's obvious here, like you have here, since that you are going more towards the speakers and the level difference is not that big, you have a lot of cancellation. But the more you move towards the side and going away from the other speaker that will interact with this one, you start getting less cancellation. So here it's dark blue, here it's baby blue, and here it's completely green, because now you are at a point, if you're standing here, you are so far from that speaker, and this speaker's interaction here is insignificant. It does not do anything. It's very low. It does not affect the signal. But the more you go towards between them, the more interactions you will have in the room. And that's for the 1 kilohertz frequency. Okay. We were just discussing the displacement of the speakers and how it will affect whether you have summation or whether you have cancellation. So in here, you have an example where you have two speakers at a given frequency. The displacement between them is equivalent to have a wavelength. So let's, for example, if you are choosing a frequency that's that the wavelength is 4 meters, if you displace the speakers between the distance between the speakers is 2 meters, so now you are half a wavelength from that for that frequency. Is that clear for everyone now, or do you need to explain it again, this part? The displacement and the relationship to the wavelength.
Can you explain one more time? Same thing?
Yeah, sure. Okay, so now we agree upon that each frequency has a wavelength, right? You have 100 hertz, or you have a 40 hertz or a 50 hertz. Sorry? So you have two speakers that are displaced, and depending on the distance between them, it's a portion or it's a percentage of a wavelength of that frequency. So for example, if we choose a frequency that has a wavelength of 4 meters, and if the distance between the two speakers is 2 meters, so the distance between the two speakers is a half a wavelength of that frequency. Is that clear?
Not exactly.
Okay. So let me see if I can. In a different color. Okay. So you have a sine wave. It's the worst sine wave anyone can draw, but it's a sine wave. Okay. So let's say we have a frequency that has a wavelength from here to here. of 4 meters. Okay, so it takes 4 meters to finish the one cycle. So one cycle will occupy 4 meters in your room. If you have 2 speakers and and the distance between them is 2 meters, that means that the distance between the speakers is exactly half a wavelength of that frequency. Is it clear now?
Yes.
This point.
Okay.
Up to this point, is it clear up to this point? Okay. So the following diagrams will show you how much does displacement, or how many wavelengths 2 speakers are displaced from each other will affect the sound. For example, if you have, so now, if you have 2 speakers that's displaced from each other, one wavelength, let's assume it's 4 meters between each other, which was the wavelength of a given frequency, what you will encounter is that you will have one lobe, you will have one area of cancellation, which will be mirrored on the other side, and then you will have another lobe of summation. And you can see them here. Whenever those 2 lines line up, this is where both have summation. So you have a speaker here that's radiating its waves, and you have another one that's radiating its waves as well. And with this diagram, you are trying to see where both will meet and where both will cancel. Okay, so in here you have the 2 speakers. Here you have them both phase locked. You have them both phase locked because this is an isosceles triangle where any place you will stand here is in exact middle between the 2 speakers. So you have here, 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 and here. Then what's going to happen? So as you move to the side, now you're going closer to that speaker and you're going away from the other one, which means that you will have a phase shift. And when we mentioned here before, you will go through an isosceles triangle, then you will go on a right angle triangle, which will cause cancellation. Then you will go into an isolation stage, which nothing will happen. Try to apply those shapes here. So you have your isosceles triangle, which is in the middle. Then you will start moving to the side, which we will go into a cancellation phase. And then you will start going into an isolation phase. What if you displace the speaker 2 wavelengths apart? So in our example, we had the one wavelength of 4 meters. So we placed the speakers with a distance of 2 meters, which is half a wavelength. Then we tried to place them 4 meters, which is 1 wavelength apart. And it caused only one gap from this side and another gap from this side. Okay, if you place them 2 wavelengths apart, what will happen? You will have your first zone, which is the summation and isosceles triangle. Then you will go into the first phase of cancellation, then another summation, and another cancellation because you are 2 wavelengths apart. So if you have 1 wavelength apart, you will have only 1 cancellation zone. If you are 2 wavelengths apart, you will have 2 cancellation zones. If you are 4 wavelengths apart, so in that case, it's 16 meters away, you will have your first lobe, 1, so you have already 1, 2, sorry, 1, 2, 3, and 4. So you have your first one here, first summation zone, you have your second summation zone, you have your third summation zone, and you have your fourth summation zone, which is a combination between both, because you are very far at this point, you are very far from this speaker, which the cancellation will not be that significant. So the further apart you take the or you place your speakers, the more gaps you will have in your response across the room. So that is why trying to keep your speakers next to each other or with a minimum displacement, or at least managing the lows when it comes to displacement, will affect how many nodes or how many cancellation nodes you will have in the room. The goal from this diagram is to let you guys understand the effect of displacement on a given space. So this speaker is radiating here, as you can see, there's one ripple. Yeah, it's radiating on the here, it's radiating here, it's radiating this side. This speaker is doing the same thing, and they are both interacting at parts in the room. Let's try to figure them out. So, as we mentioned, you need the parts where they overlap. So here you have addition, here you have addition. And at the parts where both lines are not intersecting and they are as further as they can be from each other, this is where you get your cancellation. So how far speakers are from each other will dictate how many cancellations you will have in the room. Why is that important? Let's say you are tuning a system and you are placing your microphone, and you read in front of you that you have at the, for example, the 100 hertz, you place your microphone, for example, here, and you don't know what's happening. You're just oblivious to what's happening. And you read on the data that there is no 100 hertz here, or the 100 hertz is very low. Most of the people, what they will do, they will grab an EQ, try to push the 100 hertz to rectify the issue here. But if he moved the mic to the other side, they will find that the 100 hertz is okay in this area. So now you are in front of a dilemma. What do I do? If you know nothing about system design, or you cannot visualize what's happening, you will keep running in circles. But if you take a look at the speakers and you may see, speakers are very far apart. They are too much displaced. So you go to your software while you are on the site, you put the two speakers, you put the distance between them, and you check your nodes. You will see that this is a problem that's not caused or cannot be fixed by EQ. This is a mechanical problem that you need to bring the speakers closer together. And that's why design is very important, because it can allow you to visualize what's going to happen between frequencies in the room. And once you face an issue, first thing you would do, you would try to fix it at the source. How to fix it at the source? You need to troubleshoot it properly. How to troubleshoot it properly? You need to go back to the beginning of your signal chain. So let's say there's something wrong with the 100 hertz, you check your mixer, your DG mixer. Sometimes people turn down the low knob, or they have an EQ on the DG mixer, or they have an EQ on the soundboard. You check that you don't have any EQs here or there, you check that the cables are okay. Then electronically and electricity wise, as a signal, you have nothing wrong with your processors. So you move on to the next thing, which is the speakers. How are they placed? Are they far apart? Are they next to each other? And from this point, you start deciding whether the issue are you facing is a mechanical issue or something that needs to reposition or re-angle your speakers, or it's something that can be fixed with an EQ. Is that clear so far?
Yeah, it's clear.
Okay. Perfect. Okay. You have two things that affect loss. You have as we mentioned before, how do manufacturers know the coverage pattern of the speaker? They measure it and they check on the sides where did it lose 6 dB, and that's the coverage shape. That means that the more you move off axis, the more power or the more level that you will lose, and of course it will be affected differently across different frequencies. The loss that you will have for the highs will be different than the lows, since that the highs is more directional. So the first form of signal loss or power loss or SPL loss, if you want to call it, is the off-axis loss. So you move off-axis from the center of the speaker. This is a diagram just to tell you exactly how much loss you will have if you move 45 degrees in either direction from a speaker. You can see up until the 1K, you have no loss because it's omnidirectional. The moment you hit the 1K and you start going up in frequency, the more you move towards the 45-degree angle, so the 2K will lose, for example, 2 dBs. But at the same time, when you go off axis, for the 16K, it's a different story. It lost 6 dBs. So you need to be aware that the more you go towards the sides of the speaker, the more level drop that will happen. And this is the first kind of loss that will happen in your speaker, that it's called an axial loss, because you are going off axis. So an axial loss is a loss that happens you moving off axis from the speaker. And this is a very normal thing to do, to happen, sorry. And it depends on the coverage pattern of the speaker itself. The second form of loss, it will be distance and environmental loss. As we agreed before, that the inverse square law dictates that the more you will move away from the speaker, the more level that you will lose. And you can add on top of it another effect that will dictate the rate of the loss, if you want to call it, and it's the temperature and humidity. So this is at 10 degrees. You can find, so each line with each color has a different humidity. If it's 100% humid, 70% humid, you don't need to know this, but you need to know that it's happening. It's all can be measured on the field using microphones, but I will tell you why it might get tricky in a moment. So you need to know that humidity and temperature will form a high cut filter, a natural high cut filter. So when it's 10 degrees, you will have the frequencies cut in a certain filter shape. 20 degrees, the shapes will differ at different humidity values. Same thing will happen if you go to 30 degrees temperature, different humidity values will vary. Like in here, when it's 30 degrees and it's 10% humid, you have a lot you have a lot of filtering happening. When it's 100 degrees humid and it's 30 degrees, the energy travels faster, so you don't have a lot of filtering that's happening. This is an effect that's combined with the inverse square law. The more you go away from the speaker, you will lose signal. How will you lose it across frequency is dependent by the temperature and by humidity. So to wrap it up, we have two kinds of loss. You have the axial loss by moving off axis, and you have the environmental effects and the inverse square law. Why is the environmental effects tricky? Let's say you have an event and you are installing it in the early morning. It's hot, and all of your readings and all of your tuning decisions were made, or at least you analyzed it while the temperature was affecting the signal differently, or affecting the sound level differently. Then the show starts at night. It's not as humid and it's colder. The response will change. And this is something that you need or by experience, you will know how to compensate for. But sometimes you would tune a system, go for a lunch break, uh, come back after 2 or 3 hours, and it sounds different. Why? Temperature has changed. So it's always a good practice to take a quick measurement reading before the show starts, to make sure that the effect of the environment did not affect your tuning process greatly. Another thing that might happen when you are doing an event, for example, for a club, it's an indoor club. So when you're tuning the indoor club, there are no people in it, so the temperature is different. But when people start stacking up inside the club, they start dancing, they start sweating, the temperature rises in the club and the humidity differs. So it's always a good practice that halfway through the show, you will go to the end of the venue, take a listen, see, because the only thing that will get affected is the highs, because as you can see, you have a filter, and depending on the humidity, the more humid it is, the more highs you will have. So you listen to your system quite well before the venue is filled with people, and after it's filled with people, you go again to the back and you check, did the highs response change or not? If it's too bright, it's because people are in, and it's too humid, so you need to work a bit on your filter throughout the show. If it's okay, so maybe it's not humid enough, there are not a lot of people, but something will happen definitely. So you need to check again with your ears, or preferably with the mic, halfway through the show, to see what environmental effects changed the response of your system. Any questions? Well, I hope I'm doing such a good work, since no one is asking any questions, but I doubt it. Not that good. So, okay, you have different speaker array types. Personally, I disregard the last one. The point is no one uses it, and it's, as you can see, it like you point speakers all in the same direction, and it's a mayhem of comb filtering and weird stuff that's happening. They used to do it before in the old days. No one does it now. So the main two things that you will use and you will encounter, it's either the coupled line source or uncoupled line source.
Mohammed, I have one small question.
Yes, please.
Just regarding the previous slide.
Let's do it.
You told us because of the humidity level, you have to identify the humidity level when the people comes in without the
Yes.
people. I'm talking about indoor arena. So in case we'll say
And
there's
outdoor.
a dance, yeah, outdoor as well. If there's a particular dance flow, if we talk about indoor, after we do the analyzing, if the people comes into the dance flow, again the humidity level will change, right?
Yes. That's why
Because of
you
the
have. That's
yeah,
why you find a lot of engineers who have smart running all the time, even during the show.
right, got it.
So they can monitor, and the high-end fancy amplifiers now, and everyone is trying to jump on it. So, for example, I know that L Acoustics does it. They have a temperature sensor and a humidity sensor that you can hook up to the amplifier. So it would rectify the issue, the filters in real time, depending on what's happening now in the room. Because it's not something that you can easily monitor throughout the show. Like checking the humidity levels, like you have no way of knowing that, or like measuring that. Not everyone has the tools for it. But you need to know that it's happening, and by experience, you know that it's there, and there's always a range for it. You will find it between the 1 dB and 1.5 dB. So after you spend some time in the field installing some systems and monitoring this, you will start applying that filter in the early stages of the tuning, because you know, yeah, now it does not sound bright, but I know when people will come in, it will increase in the highs and like in the 1 dB, so it's better to take it off now. So it's something that you will know by practice, or if you have the equipment or the fancy new amplifiers for it. Other than this, you need to keep it in mind and you need to check it until you understand exactly how it happens and how it sounds. I know it's a bit tricky, and I know that this field is filled with uncertainty because everything is playing against you, but you now have like a basic grasp of what can change the sound during a show. You need just to monitor it, bear it in mind, work on it for a while until you know how to hear it during an event. I answer your question, or do you have another one?
Thank you. Thank you.
You're welcome. Please, guys, any questions you have, just keep them coming. Okay, so you have the coupled and you have the uncoupled line and point sources. And it's from the name. Coupled, they are next to each other, no gaps between. Uncoupled, you have gaps between. Point source, they are not overlapping, as you can see. They all act as if it's a one big speaker and as if the speaker point is why it's called point source, because when you put the speakers next to each other, they create a virtual speaker right behind them. And it acts as if it's a one big speaker with a extended coverage angle. And this is like a perfect example on using summation of the lows to your benefit and isolation of the highs to your benefit. So when you place, so we discussed before that displacing the speakers will affect the summation zones on what's going to happen, especially in the low frequencies. But since that the low frequencies are huge, like huge in wavelength, so when you place the speakers right next to each other, you don't have the enough distance to create a phase shift that will affect the low frequencies. And you have the perfect isolation because the speakers are not overlapping for the highs. So by this, you harnessed the power of isolation for the highs, and you used minimum displacement for the speakers to harness the power of summation for the lows. So you create a big speaker with the minimum variance. Is this clear?
Yes, clear.
Okay, so you have point sources, uncoupled. It's the same thing, but the decisive factor here is the displacement between the speakers and how much it's going to affect which frequencies depending on that displacement. Same thing here. They will overlap somewhere, but they won't overlap in here. They all have different applications. We will discuss the basic forms of them in the upcoming slides. Okay. So, perception. How does your brain works in terms of, especially in localizing sound? This is very important. So you have two speakers, one that's emitting sound from the left side, and there's another one that's emitting sound from the right side, but somehow we hear them coming from the middle. Crazy, right? How does that happen? It happens because of sound localization. So to be able to localize sound horizontally, so let's say that you have a sound that's coming from this direction. Sorry. Let's work with the basic one first before we go this. So we have the sound coming from the center. So the time, so throughout your growing up since you were a kid, your brain has been collecting data and been working with it. One of those data is the distance between your two ears. If you want to know a position of something, you need to have a triangle. It's called triangulation for a reason. So if your brain knows the distance between your ears because it's been hearing voices since you were a kid, trying to localize them, trying to know where they are, and it builds a map that it works from distance maps. So it knows the difference between both of your ears, and the sound is playing here from this side. So the left side or the left ear, your brain will process the information for each ear on its own. So it will check, it will know the distance from here, and it will know from the other side it's coming, it's taking this amount of time, and it already knows the distance between them. So forming a triangle, your brain will tell you, yeah, the sound is coming from this side. So why do you hear the sound coming in the center? Because if you have two, so you have a speaker on this side, you have a speaker on this side, and they are both sending you timing information that is it's completely just a moment, I cannot do two things at the same time. You have two speakers that's sending the same timing information because they are both placed in the same distance. So it's taking, for example, 5 milliseconds for this sound to reach, and it's taking the same exact signal. It's taking 5 milliseconds to reach this ear. So your brain does not know what to tell you. Is it coming from this side or it's coming from this side? So it chooses a compromise, which is in the middle. It tells you, yeah, it's coming from here, from the middle part between the speakers, because it's getting a timing information that's identical from the right and from the left. So it does not know what to tell you. Is it coming from here or there? So it points towards the middle. And this is how stereo field works. So the moment you start increasing the volume on one side, that becomes louder. So your brain will start localizing the sound towards the louder speaker or the louder object. And this is exactly what the pan pot on your mixer or your DAW or anything does. All it does is that it sends more level to the left or to the right of the speaker, and depending on that level, your sound will start localizing the sound towards the higher level. So you pan it all the way to the right, so there is no sound on the left side of the speaker, it's only on the right. You say, yes, it's coming from this side. You move it a bit to the left, you move the knob a bit to the left, so it's sending some of the speaker volume, the sound volume to the left speaker, some of it here, and it's higher on this side. So you will think, because you are getting different level cues, but the same timing cues, you will feel that it's coming from somewhere in between. The more you go to the left, the more it will send level to the left. Same thing will happen to the right, and according to the level difference, your brain will tell you, yeah, the sound is coming from this side or that side. Is this clear for everyone?
Yeah.
Okay. So how does this work in a bigger setting? So to be able to listen in stereo, you need to be able to hear what's coming out of the two speakers, right? And we said that the pan pot works that it changes the level either to the left side or either to the right side. So if you are a listener in a venue and you're standing close to the stage, you can now hear a lot of the right speaker and a lot of the left speaker. So now the stereo field is very visible because you can have level data and timing data from the two speakers. No speaker is dominating the other in terms of level, and no one is leading the other in terms of time. So you have a very wide stereo field. The more you go backwards in the venue, the stereo field will decrease. So the person who's standing in the front will be able to have a wider stereo field, while the person standing in the back will have a smaller stereo field. That's why it's good practice when you are standing FOA mixing show, not to pan the sounds extremely right or extremely left. Why? Because not everyone is standing in the middle. You have people that's standing on the side. So if someone is standing on that side and you pan a signal or you pan a sound completely to the left, it will be very hard for him to hear it because it's being dominated by the other speaker. So changing your listening position in the venue will affect how stereo you will hear the sound is. So you need to make sure that, especially in the mixing decisions, that the stereo field will keep changing over space. If you're standing here, you will feel that the stereo field is coming from this side and it's narrow. If you're here, it's wider, but it's not that center. So it's very important not to pan stuff right and left, hard right and hard left, to be able, at least for people who are standing on this side of the venue, to be able to hear what's happening and not to miss some stuff of your show. This is pretty much about the stereo field. It just gets narrower every time you go to the back. Of course, there's more to talk about the subject, but this is what you need to know for now, because it won't affect your decisions that much. Okay, so regarding stereo, is everyone on the same page here? Any questions? Okay, so this is the most important thing that you want to take as a decision when designing a system. You want minimum variance or you want maximum SPL. To be able to take that decision, you need to know how pointing or how angling a speaker will affect the listening area. So it's a good practice when you are designing a speaker. So let's say you have here a slope or something that has a lot of people sitting like in different levels. Okay, so it's a good rule of thumb is to point the center of the speaker towards the end or the furthest part in the listening area, and let the pattern of the speaker itself do the rest. How it's going to do that? You have two methods. It's either you go for minimum variance or you go to maximum SPL. To go to maximum SPL, you just point the speaker towards the center part of the listening area. So what's going to happen? As you can see here, each change in color is a, it's not mentioned here, is a 6 dB, sorry, it's a 6 dB reduction or a 6 dB difference in level. So if you are standing in the B, in the this, I don't know what the color is, it's not baby blue, it's brighter than this. So if you're standing here, the difference between here and here is a 6 dB in change, which is a very high variance. You have a listening position that's louder, for example, 6 dBs than a position next to it. So yes, you can get another speaker, put it next to it to be able to send more power to this side, and you can put another speaker under it to send more power to the bottom side of the listening area. But what's going to happen? You will have an interaction that will happen inherently between the three speakers, because any speaker will have the summation zones and they will have their cancellation zones. So what's going to happen is that you will have, yes, you will have more power, but you will have a lot of frequency variance across the listening area, because you will have a part where it has a cancellation, you have a part where it has a summation, and then another cancellation, then isolation. So across the listening area, you will have a lot of spots where it have a lot of variance. But this is the price you pay when you want maximum SPL. You point a lot of speakers in that area, but they will interact together, so you will have a lot of frequency changes. If you are okay with that, like for example, I know, for example, some of our clients, all they care about, because some of the techno events, all they care about, we want more SPL. The louder, the better. We don't care that much about frequency changes. We don't care much about that. We just want our event to be louder. So we normally, of course, that comes with a price because we will send more speakers. So the client is already okay with variances. He does not care that much about the intelligibility of the sound. He just wants a banging event with a very loud noise. So in this case, he will start putting more speakers. But let's say you go to someone who wants a more a uniform, or he wants a better sound quality for his event. You will start using the minimum variance technique. Why it's called minimum variance? So we agreed that a coverage angle is a point where it loses 6 dB on the side of the speaker. So if you look at the coverage pattern, you will find that in front of the speaker in the center, it's louder 6 dBs than the side, which is at 0 dB. Then you will double your distance, which will cause an inverse square loss of 6 dB. So at this point, it's 0 dB. And on the side, since that you will apply the inverse square law on the side of the speaker, the negative 6 dB that dictates the coverage pattern of a speaker. Okay? So up until this point, we are standing here, which is 0 dB, like center of the speaker, and it's less 6 dBs on the side. You, of course, you don't do that. No one does it now like manually. You have a software to do this. You will check where the inverse square law will affect the center of the speaker. So I know it's a bit confusing. So you have here the 0 dB. Let's dissect this into two parts. The first part, the on-axis part, and the second part is the off-axis part. So the on-axis part, you have 0 dB, and if you double the distance, you will lose another 6 dB. So at this point, it's negative 6 dB down. And we agreed that a coverage pattern off-axis is dictated when it loses negative 6 dB to the side. So now you have 2 points in space. A point that's affected by the inverse square law and the environmental loss, which we will call it air loss. So you have a point where it lost 6 dB because of air loss, and you have a point that lost another 6 dB because of the axial or the off-axis loss. If you draw a line between the 2 points, you will have an area in the coverage pattern with the minimum changes or the minimum losses possible, because you're moving from negative 6 to negative 6. And you can see it here in the diagram. This is the listening area. The listening area is all located in a place with the same color. There's no difference. Up when you compare it with this, like let's take like all of the listening area here is in one color. It's in the same 3 dB variance range, while it's the same listening area in this part. Can everyone hear me? Because my I have internet.
Yeah, we can hear you.
Okay, so when you point the speaker directly towards the center of the listening area, you will have an area here that's different than here, and different than here. So you have maximum SPL, but you have maximum variance. While when you are using the minimum variance method, yes, you won't get it as loud as you will get it here, but you will get a uniform response across the listening area. Everyone is in the same variance level. Everyone is enjoying the same loudness or the SPL as everyone else in the listening area, which is apart from the maximum SPL formula. Do you guys understand this, or do you need to explain it? And please, if you have questions regarding this, please let me know. Okay.
It's clear.
Sorry?
It's clear.
It's clear. Okay. Subwoofers. Okay, subwoofers is a very wide topic. Today we will touch on the very basics of the subwoofers and how to do two variation or two different setups of subwoofers. And if you are guys interested, we can in the future make another class for subwoofers to talk about them more.
Yes, please.
Okay, so basic directivity rule. If you have a small diaphragm or you have a small driver, you will not affect directivity a lot. But if you have a large driver, it will compress the wave and it will make it narrower. Okay? So, how to achieve this? Using subwoofer arrays. Subwoofer arrays are practically you put the subwoofers next to each other to be able to form a one big subwoofer. You can create the largest driver there, so you can start compressing the energy and you start directing it. So it's very hard to direct or to steer subwoofer or like big frequencies, like low frequencies, like 3 meters and 4 meters wavelength frequencies. It's not impossible, it's doable, but you need to know what you're doing, because you can play with phase all day to start steering the subwoofer, since that any change in phase can be noticed on the lower frequencies easier than being noticed on the higher frequencies. For example, imagine those are 3 subwoofers in one line of what's going to happen. So they will all concentrate their energy towards the front. As you can see on the sides here, they won't affect, and the reason why it will be cancelled on the side, it's a big topic, but you need to know that the more you add, the more cancellation will happen on the sides, and the most of your energy will be directed to the front. Let's say you want to extend the coverage pattern to the sides. To do this, there's something called steering. It can be done mechanically, like by changing the positions of the subwoofers, or it can be done in an amplifier, like in a DSP. And this is the option everyone does it these days. To use the amplifier by using different delay values to change the coverage pattern. How to do this? So let's say you have 4 speakers. You will delay, if you have a center subwoofer, you will delay the one next to it with a fixed value. You will delay the one after it with a greater value. You will delay the one at the end with a greater value, which will start doing something called steering. As you can see here, all of your energy was directed to the front. But once you started applying the steering values, the coverage range started expanding towards the sides of the of whatever venue or whatever you are using the subwoofers in. How to know those values? Most of the prediction softwares these days have that option. You just let me see. So for example, I will add a subwoofer, or I want to add a speaker here. The software is asking me, do you have a subwoofer array or it's a standard setup? I would tell him no, it's a subwoofer array. And I want the VOID Acoustics. I'll place my subwoofer here. It will ask you how many boxes do you have. You will tell, yeah, I have 10 boxes and I'm spacing them. I know for a fact that this number is the exact number, so the subwoofers would be very close to each other. So you will tell the software, yeah, I have 10 boxes and I want them to be spaced to 1.3 meter, 0.35 centimeter apart from each other. And I want the coverage angle to be 40 degrees, for example. It's taking some time to render. So it will give you the delay values that you will need to apply on your subwoofer. So the middle boxes will be 0, the one next to it 0 0.1, 0 0.6, 1.6, 3.4. And those values will allow you to achieve a 40-degree of coverage angle using 10 subwoofers with a spacing of 1.35 between them. Let's say you increase the spacing and you want a wider coverage angle. It now will change the values and it will tell you that you need to delay the subwoofers next to each other with those exact values to be able to get this kind of coverage angle. Most of the prediction softwares have it. You don't need to do the calculations for yourself because it's very hectic, and everyone uses them. So the part about steering, is it clear?
Yes.
Okay. After the session, I will ask Max to send you guys some links. One of them is a guide from VOID on how subwoofer works. So you have, if you don't have a software and you want to understand more, they have a lot of examples. What if you put the subwoofers in an arc? What's going to happen? What if this arc is inverted? What's going to happen? If it's in a straight line, what's going to happen? So it's a decent guide. It will give you an overview on how your subwoofers how you want your subwoofers. So for example, let's say you have a I can't find the situation where this would be so let's say you have here an artist or you have a microphone of some sorts and the dance floor is in this area and you don't want to push subwoofers to this side, so you can use this configuration because you won't have subwoofer here, but you will have subwoofer in this area to be able to steer your low frequency towards the coverage pattern that you want for your design. A very common setup is called the cardioid array. So the cardioid array, it uses the phase, you use the cancellation to your benefit. So how it's set up, you would have a subwoofer, of course, and that can be done on a wider array, but this is just to show you how interaction speaker to speaker is going to happen. So you have a subwoofer that's facing the front, and you will have another subwoofer that's facing the back, and it will be sitting on top of it. Using tuning techniques, the ultimate goal is to have this subwoofer fire towards the back at the moment. Okay, so let's agree. Subwoofers, they have omnidirectional pattern. Okay, so you will have sound radiating in the back and in the front. If you have a subwoofer that's facing the back of the other subwoofer and you time it where the top subwoofer fires at the moment where the radiation at the back is 180 degree out of shift, you will have a cancellation that's going to happen in the back and it will stay the same in the front. Why is this useful? It's useful to be able to reduce stage noise. So you have a band in a big event, you have a huge arena, you have like 30, 40 subwoofers in front of the stage. It will affect the artists. It will make everything rattle. It will affect the mics. It will cause the artists, they won't be able to hear themselves in the monitor, so they will ask a higher monitoring level. which will affect the sound going to the front. So in order to avoid this, you want to keep your stage as clean as possible from noise or like of unwanted frequencies. Since that high frequencies is directional, so it's easy, but for the low, it's omnidirectional. So you use a cardioid array to be able to cancel some of the frequencies that's going in the back, thus keeping your stage clear of noise. Is this clear?
Yeah, clear.
Okay. Any question, guys? Anyone want to write a question in the chat or anything? So I have a question here. It says, how do we get to know what side is going to cancel out from phase shifting in this particular array? Nice question. Okay, so I'll try to draw it quickly here, but there's another, like, can do it sometime later. So you have your bottom box. It's firing in this direction. And it will radiate the sound towards the back. You have the distance of the box itself. So normally the distance of the box is usually around quarter a wavelength of the center frequency of the subwoofer. So not to get into a lot of technical terms, so let's assume that the driver in here, you will have sound that's going this way, but you will have sound that's going that way. You have another subwoofer on top. The driver is looking this way. Normally, in the tuning process, you will delay the top subwoofer, so it will match the time of the front subwoofer. Sorry, the front driver. So what's gonna happen? You will delay it as if it's virtually on this side. So this will fire, this will fire, and the moment it reaches here, this driver will fire. If you can see here that you are already towards 180 phase shift for the back firing, or for the energy that's going towards the back of the subwoofer. So if you start from here, it's around 180. That's the moment where the top driver will fire. And since that it will fire at a point where it's exactly 180 degrees from the energy that's coming out of the back, since that we have the same level because they are on top of each other. So you have, let's think about it. What's the relative level? Relative level is 0 because they are both on top of each other. Okay, so I might have an addition or I might have a cancellation. What's going to decide whether I will have an addition or a subtract or a cancellation? It's the phase. What's my relative phase between the two boxes? At this point here, where the driver will fire, you are 180 degrees out of phase. So since that you are 180 degrees out of phase and the relative level is 0 or like something very small, so you will have complete cancellation. So what's going to happen is the waves coming from the back is in complete cancellation, and in the front is not affected, since that this driver is firing at the same exact moment that the one in the front is firing. So you have addition in the front and you have cancellation in the back. Is this clear? Or do you need me to explain it again? Okay, let's move on. Guys, I'm proud of you. You nearly pushed through it. Okay. So let's say you got a chance to go volunteer, or you got a small gig, someone hit you up, you know what, I know you do audio, I have a small gig and I want to design a system for. I'll share like a very basic installation setup and a way to think on how to do it. That will help you to do events up to 1,000, 2,000, maybe 5,000 attendees, depending whether we can push through the line array segment towards the end of the session. So someone hits you up, you tell you, well, you know what, this is the stage, and this is my audience seating area. I want you to do the sound for this event. As we agreed in the beginning, it's all about geometry. You have a space, and you have speakers with different coverages, and you need to make sure that you don't have any gaps in this. This is an oversimplification for the topic, but in an essence, this is what you're trying to do. You're trying to fill the space with sound, and you have different geometrical shapes to do that. So you will check the audience seating area. You will check your stage. You will know that this is the area that you want to cover. So you will start, first of all, with your main speakers. In this example, it's not line arrays. It's just two normal, like our main speakers will be two speakers that's being flown. It's not line array. It's a point source speakers. And I'll show you how to that you can design with those speakers. So first thing, you have your right side. You dissect your audience area into two halves. You have on the right side, you will put a main speaker, which is called the outer fill. And you will put one next to it, what's called an inner fill. And if you can see now, you have filled this area. You fill this area. The way I see it, I would think of it logically. So now I have this area covered. I have this area covered. This speaker is flown. So beneath that speaker is a gap because it will be pointed towards nearly the end of the venue and towards the middle part of the venue. So I see that there's a gap in here. I see that there's a gap on the side. I see that there is a gap on the other side. So I identified three possible gaps: the center gap, side gaps, and the gap under the speakers, the main speakers. So my next step will be start to fill in those gaps. So I will start by adding the side fills. You will add a side fill to be able to cover this side. Same thing applies here. So if you take another look, you manage to cover this area, this area, this area, same thing here. The way I see it, what's missing is the center part, because this has no sound, since that the two speakers, main speakers, would intersect at this point. Beneath those speakers, since that those speakers are flown, so you will have a gap that you will need to fill with another speaker. This is the middle area that you need. So a gap in front of the main coverage. Main system is flown, so there's a coverage gap beneath. Same thing on the other side. This calls in for the front fill system. You have the center fills. You have a fill that will go beneath the speakers to cover the gap. You have another one to go here. Disregard this for a second now. Sorry. So now you have speakers that's covering the middle. You have a speaker, I don't know if you can see the coverage lines, that's beneath the main speakers. You have all of this covered. Depending on the space itself, just say you have a huge space and you check on the prediction map and you find that you will start losing a lot of SPL from this point because inverse square law played this turn, and now you don't have enough power to push more. It comes for a time for a delay system. You put other smaller speakers towards the back. You can hang them. You can put them on stick. Depends on what you have in your warehouse. So you have a delay system that will complement your main system, so it can restore some of the level and store some of the frequency intelligibility towards the back of the venue. You add subwoofers. So in most events, especially corporate and mid to small sized events, people hate putting subwoofers in the front. They just want them on the side, not to not to be in front of the screens and people whoever is talking, so they don't like how they look. But in a bigger event, you will definitely need to put subwoofers in the front. But in here, you put them on the side in this example because it's a small event. So you know, at least when you're doing the prediction, you have two subwoofers. It's greatly displaced. You take a look at the subs, what's going to happen. You check the nodes, you see what's going to happen. If it's acceptable, it's okay. If it's not acceptable, you politely just tell the event promoter that, you know what, we check the predictions and you will have some gaps or you have some spots in here, here, and here. If he's okay with it, that's okay. And you need to bear in mind something. For example, if you are designing a system for a corporate event where people will talk and stuff like this, you don't need perfect subwoofer coverage because people be talking all the time. They will have the music that's being played is just background music between the shows, something like this. But if you have like a full-on EDM event, you will need subwoofer properly to be placed everywhere. So depending on the program material will give you some flexibility on how you can sacrifice some of the intelligibility or some of your response in the room in favor of building good relationship with the event promoters, because still you want to get paid, you have bills to pay, you want people to give you a call. So if they want you to move the subwoofers 2 meters and it's already 14 meters apart, what's the damage? It's already been that you have a lot of gaps already. So yeah, you can move them that meter or 2 meter in favor of just being a flexible guy. But if it will cause something extremely a huge issue, you just tell them respectfully, you know what, this will cause 1, 2, 3, 4. And depending on your company's policy, some companies won't accept it because they have an image that they want to keep and some sound signature that they want to keep. You say, you know what, this is against our policy. But if your boss is okay with it, so yeah, you can do it in just building good rapport with different event promoters. So this is a basic system design or how to think on creating a system or designing a system for a space. This is scalable on any venue. Like you just need to know where the audience will be and you need to think how I'm going to put in the speakers to be able to fill in the coverage that's in front. So up until this point, do you have any questions, guys? Okay. Line arrays. So I'll touch quickly on line arrays because it's a topic of its own, but I'll try to simplify the theory behind it. Line arrays is a clear demonstration on how using or harnessing the power of low summation and getting the useful benefits of isolation in highs. So the power of the line array is that it acts as if it's a one huge big speaker. Having the lows or having the boxes very close to each other will ensure that you will have maximum summation in the lows area. And since that the speakers itself in terms of the high are very narrow, like you're talking about, for example, the arcline speaker has a coverage angle, vertical coverage angle of 3 degrees, only 1.5 degree either up or down. That's very narrow. That's very, very narrow. Why? Because do you want to be able to harness the power of isolation when it comes to the highs? But since that the boxes are next to each other, you will get maximum addition in the lows. So you will have one big huge speaker that pushes mids towards everywhere in the dance floor, and you have highs that you will assign using the angles of the speaker to be able to assign a cluster of speaker to each part of the venue. So I'll show you this in the software now, but let's go to the rigging after we finish this. So this is a line array. This is a 50-meter deep venue. So as you can see, each speaker has a center line, and each speaker can be changed with an angle. If you look at the speaker at the bottom, if I change the rigging angle, I'll be able to control which speaker covers which part of the venue. When designing line arrays, there is a good guideline that you would start with. We cannot go deeper in that because it will take more time, but this is a very quick way to design line arrays. You need two things. First thing, there's something called overshooting. Overshooting is, so let's predict. So you have two speakers on, you have your whole tower. As you can see, the tower did not start developing. I'll tell you something, let's go lower in frequency. So you have two speakers on top, but it's taking some time, or it's taking like the first two boxes for the array to start developing, because a behavior of the array is the combined behavior of all the speakers working together. So it will start gradually progressing. As you can see here, you have two speakers on top, but you have a change in the level. It's called the level contour. So you have a change here, but the more you go towards the center of the tower itself, the more increased effect that it will have on across a lot of frequencies, depending on the angle and depending on how it's flown. So there's something called overshooting, and it's mainly you aim the first two boxes right on top of the people height. So normally people would stand around 1.7 meters. Of course, it would vary from one person to other, but the average is 1.7 meter. Each box here, each grid box is 1 meter. So the people will be standing nearly towards the first two boxes, two grid lines. So if you want to overshoot the first two boxes, you want them to be somewhere in the third meter here to start overshooting properly. So you can overshoot. So we can start first by giving some sort of a tilt to the tower. Then you go back to check. You are still way on top, so we can tilt it more. So you need to tilt it, for example, more. So now our target was to overshoot on the third box, a third grid line. So I see here that you need the first two to be here. So it's a good idea to lower the tower a bit. So for example, instead of having it at 9 meters, let's see if when we have it at 8 meters. So 1, 2, 3. Yeah, it's a good starting point. Then you want the distance between each speaker and the other to be as equal as possible on the grid here. So the distances between each one is roughly the same. Why they are doing this? I'll explain it quickly. So we said if you want maximum SPL, you want to direct a lot of speakers towards that point. And since that you will have a lot of loss more the further you will go deeper into the venue. So the maximum air loss will be towards the back because it's the furthest point in the venue. So that's why you need to point a lot of speakers from the tower towards that point and then gradually pointing less and less speakers towards the front. So what's going to happen? You will have a lot of SPL pushing towards the back, less SPL pushing towards the front, so they somehow level up. So you will have some sort of a uniform response across the venue because you have a lot of speakers pushing a lot of sound to the back because of the air loss, and you have speakers that's pushing less SPL towards the front since the people would be near the tower itself. So you don't need to push as much SPL, you're pushing towards the back. And you just predict this is the 1K. You will find that you have a gradual response towards the back. Let's check a higher frequency, 4K. Still, you have the 2 meters here. You have a gradual response that's going towards the back. And with prediction softwares, you can place microphones. So I have a microphone here somewhere. Wait just a moment. This I have a microphone that's 10 meters away from the speaker. You have another microphone that's 20 meters away, another one that's 30 meters, another one that's 40 meters. All the prediction softwares will offer this option to have a measurement microphone so you can check the responses in Map 3D. This is where you can check it. So I have microphone 1 that's showing me that's 10 meters away from the tower, and as you can see we have a nearly perfect response. Just a build up in the mid here, a small one that can be equalized. Check the microphone at 20 meters. You have a build up here that can be equalized. This is something that you will know a bit by experience. There will be equalized in here. You can either raise the high frequencies or lower this. Those are decisions, tuning decisions. It's not our topic today. Number 3, a very good response. That's from 30 meters. 40 meters, you have a very good response. So now, as you can see, for a distance of 40 meters, you manage to get a nearly uniform response across the venue, which can be rectified with very small EQ touches. And this is the power of the design. If you design your speaker or your system correctly, you will not need to use a lot of tuning and you won't spend a lot of time tuning your system because you did your job on calculating the air loss, you did your job on calculating the positions of the speakers, you did everything in the design phase. So to wrap it up here, get your tower, overshoot above the people, make sure the lines are equal, somehow equal, and bam, you have a line array system that works. With bigger line arrays, with bigger towers, you need to consult with the truss department, because you have different ways to rig a line array system. You can put it in a scaffolding. It can be used inside a goal truss, or you have line array stands that you can use. Always, always, always for the lines, for the stands, you need to consult the manual to know the maximum weight that it can handle, so it won't fall or break. If you are rigging it with a gold truss or a scaffolding, you need to consult the truss department and the rigging department. You need to tell them, of course, you will get the information from the manual. You get the weight of each and every speaker, you calculate them, you put around 15% or 25% extra just to be on the safe side. You tell him, you know what, I have 500 kilograms of speakers. Will your truss be able to handle it? You get the clear from the rigging guys, it's okay. You can start rigging them. Normally, you use a motor that goes into the frame on top, and then it's a motorized one, and you're good to go. You just need to make sure that the height is as same as the one that you decided in the prediction software. Make sure that you deployed it correctly, then start doing your tuning. There's another form of using line arrays. For example, this is one that you have a very low ceiling. So, and they don't have a budget, for example, to get a truss, to get something like this. Some people will ask you to stack it. I see that it's a complete waste of money, because you have two speakers on top. Normally, the case is you have two speakers on top that's not pointed anywhere. It's pointed in the air, where no one is there to listen. So technically, you use or you benefit from the lower speakers, and once people start dancing in front of them and stacking up in front of them, you will lose high frequencies in the middle, and it will sound lower in level, and it's a complete disaster. So I try always to push for flying and rigging the speakers and hang them. If you cannot, and that's the case, you need to know that somehow during your show, the middle part of the venue will lack highs, because people will be stacked in front of the speakers and they will block it. But some event organizers does not care. Again, you want to pay the bills. You need to know, because if you go throughout the half of your event and you say, come on, it did not sound like this in the middle when I was tuning it, when it was empty, it's because people are standing in front of it. So you need to know that's something that you cannot fix. You don't try to increase the volume, or you don't try to reach for an EQ. It's a fact. People are standing in front of the speaker. This is a reality that you're living in. So up until this point, I finished the theoretical part. The upcoming part is just getting you prepared if you have an event, what to do very quickly. So please, if you have any questions regarding any part, please ask it. Okay. So any event, for example, your boss gives you a call, you know, Matt, you have an event. This is a number for the event promoter. Deal with it. First thing you will call the event promoter, and you will ask for the advancement documents. The advancement documents usually include a plan for the venue and includes the technical rider. So, for example, I have an example here from something that I'm designing soon. So this is the advancement document. They are giving me the dimensions of the place, where the regular crowd will be, where the VIP lounges will be. You have dimensions, you have stuff like this. And if they are using AutoCAD or SketchUp, most of the prediction tools can export SketchUp data or CAD data, so you don't have to draw anything. Other than this, what I normally do, because sometimes I get lazy, I see, okay, it's a 50 by 50. I don't draw anything else. I know what's going to happen. And then by experience, I know what to do. So you check the plan. Normally, if you have a PDF or you have like a 2D rendering, like the one that you're looking at, it does not have information about the ceiling. So as a good, if it's an outdoor thing, it's okay. You just need to check if you have a truss to hang your speakers on or not, and you're okay. But if it's an indoor one, it might get tricky. So I prefer, personally, after I receive the advancement papers, I do a site visit. You need to check a lot of things. You need to check what's your electricity source. Is it from the building or it's a generator? You need to know where the loading dock is, because you need to estimate how long it's going to take you to get your equipment into the venue. You need to check the working hours. When are you allowed? Because it might be an hotel that you're doing a corporate event for, but you might have a wedding that's happening in a hall next to you, so you're not allowed to have any technicians or anyone working during that time of the event. So you need to check exactly when can you work. You need to check the height of the ceiling to see how high it is and whether you can find any points that you can rig or you can fly your speakers on. You need to check for obstacles. We once encountered an issue that they sent us a plan, and we wanted a site visit, but it took them a lot to arrange it. And when we went, it was like 2 or 3 days before the event, and we had already a plan in mind where to put the speakers from the drawings. And guess what? We found a huge palm tree where we want to put our speaker. So it's always good to either have a video of the place or to go visit it yourself to see what natural obstacles are there that will not appear on paper. You need to check where the mixer location is. You need to check where you will put your mixes, stuff like this. After that, you need to check your rider, the technical rider, and the technical rider normally has a lot of very important information. And a normal technical rider will look something like this. They will tell you when the sound check time is, what kind or acceptable models for the main PA, what's the recommended, what they normally are okay to use or to work with, what's the preferred digital mixer, what kind of in-ear monitors do you want. You will know a lot of information about what kind of drum kit, which amplifiers for the bass, keyboard, stuff like this. It will have a patch list, how to name things on the mixer, and what kind of microphones do you need on each channel, whether it's a DI, it's a wireless microphone. It will have a table that has a patch for the monitoring, if you have for the monitoring desk, so which outputs for the drums, bass, stuff like this. And it will have something like a stage plot where it tells you exactly, okay, the drum kit will go here, the keyboard in here, guitar, so you can start working on your cabling and stuff like that. So you need to know this information from the technical rider. It's very important to have it, and every artist have it, or if they don't, they should. It's very important to check the technical rider. So after you check the technical rider, check the everything, you start checking your plans, checking the drawings, start putting in a design in your head. It's a very good thing, or it's a good practice to, when you're doing the site visit, go stand in the furthest point in the venue and start visualizing an event. People are dancing here, there, I will need speakers here. Start visualizing how this space in an event will be and where do you want your speakers to go. It's a very good mental exercise. So when you go back home or you go back to the office, you start working on your design plan. You need, after you work on the design, you need to work on amplification. So you have passive speakers, you have active speakers. If it's passive, how many amplifiers do you want? How are you going to connect them? You need to do a plan for the amplification process. Then you need to do a DSP management plan. So which speakers are you going to connect together? So how are you going to send signal to that cluster of speakers? How are you going to send the signal to the delays? How are you going to send signal to subwoofers? You need to know exactly how you are going to connect your equipment. We mentioned the technical radar requirements. You need to work on networking because, as we mentioned, it's very important that you know a lot uh, about network protocols, and a lot of people are using Dante or AVB, and this requires a solid networking infrastructure. And since that sometimes you will stand 40 or 50 meters away from your processors, you need to talk with them through your laptop or iPad or whatever. So you need to have a switch on that side, a switch on your side. You have a Wi-Fi router on your side, so you have an iPad, for example, to control things. You need to set up the Dante network properly. So you need to know before you go how you will handle networking and communication between your equipment. Then you need to work on your electrical plan. So where's the electrical source, where you are going to place the distribution box, how you are going to send the electricity to your amplifiers, stuff like that. And this is the kind of thing that you prepare back at the office. Let's move to the day of the event itself. It goes as follows. Loading in, you go in, the cars will start loading in all the equipment. First thing to do, you hook up the distribution box. You need electricity. So you make sure that the distro box is connected properly. You make sure that, because all distribution boxes, they have meters in front of you telling you what's the volts, what's the amperes, stuff like this. You need to make sure, for example, in my country, we use 220 volts. We need to make sure that it's within range. Sometimes it goes to 230, 210, but all equipment have tolerance for this, and you need to check it in the manual. So you make sure that the electricity is stable, nothing is wrong, everything is working. Then you start working on deployment, hanging the speakers, putting the subwoofers, putting the subsystems that you will do, whether it's front fills, delays, or stuff like this. Once you start hacking them, you start connecting them. This is the cabling process. You need to start connecting whatever's on the stage, amplifiers. You need to, the microphones, stuff like this. You need to make sure that all of the cabling is done, whether it's for the PA system, whether it's for your FOH mixers, monitors, stuff like this. You need to make sure that the stage is set up, because you have a guitarist who wants an electric plug in front of him. He has 40,000 guitar pedals and stuff. So you need to make sure that everyone has electricity, everyone has his monitor in front of him, everything is powered, no one wants any extra electricity or cables. Then you go to set up FOH monitoring and you start building rapport. If you are working, okay, so at the beginning of my job, I used to do system engineering, front of house mixing, and monitoring at the same time. Sometimes they want this or that, and I see that it's important for an engineer to know how to do all of them. You can specialize in something, but you need to have an idea about what's happening in the others. Let's say you are a system engineer and there's a front of house mixing engineer that's coming in that you don't know about. It's very important to build good rapport with the guy, because you both have the same goal, to have a good show. So you are superior in the knowledge of what's happening in the room, stuff like this. You find that halfway through the show, he's reaching for an EQ for the 400 hertz. You tell him, you know what, I know because of the speakers that there might be an issue here, or there might be an excessive summation, for example, at the 400. Let me check if it's happening somewhere else in the venue. You go, you check, you come back, you tell him, you know what, it's only happening here. So whenever you hear something's wrong with the 400, just ignore it, because it's happening at this position only. So it's a very good thing to have a nice and decent relationship with the people you're working with, to achieve the goal that you want to achieve. After you finish setting up FOH, building rapport, making sure that you're all on the same page, you start system verification. You start the line check, make sure all the mics are working, because as a systems engineer, you need to make sure that all the systems are working. So microphones, keyboards, your PA system, mixers, stuff like this. Once you make sure that the system is verified, then you've done a line check, you start tuning. After you finish tuning, you do a complete rehearsal for the show and make sure that you are ready to go for the event. Any questions, my friends? I think I talked
Everyone's
everyone
quiet.
to sleep.
Any questions, guys?
Any questions?
Mahmoud, can we get a copy of that technical rider you showed us?
Yeah, sure.
Thank you.
You're welcome. What else you guys need? I'll send you some links. I'll send you the technical writers. What else do you guys need from me? Anything? Any question?
Can we get a contact detail of you?
Yes, of course. Max has my contact. We have my email, WhatsApp. Just whenever anything you want to ask about, hit me up.
Yeah,
I'm happy to talk about this stuff all day long.
Yeah, I can pass that on.
Thanks.
I'm sorry, I couldn't. I wanted to introduce Mahmoud properly at the beginning, but I got caught up a little bit.
I'm
But
glad we did this.
yeah. So again, thank you so much, Dabbous, for dropping
Anytime.
into. Yeah,
Thank you very much for having me.
yeah, and I hope
you guys
everyone,
got it.
yeah, got something out of it. I think we went over a lot of things.
Yes, I was
Yeah.
so afraid I won't be able. Like I got carried away. It's like more 30 minutes, but at least we got it done.
Yeah,
I'm
that's
happy
good.
we did this.
Yeah, that's good. Oh, thank you so much.
So
Thank you
thank
so much.
you very much,
And
everyone.
maybe you could go for another session if you're
Yes, please.
yeah,
If they are up
another day,
for it.
yeah. If
If they're
everyone's
not bored to
interested.
death. Yeah, if they're not bored to death.
Yeah.
Okay.
Yeah.
Set
Thank
it
you
up
guys.
and let
Thank
me
you.
know.
Everyone.
Thank you,
Enjoy.
guys. See you soon.
Yeah.
Have a nice day.
Thanks, man. Bye.
Bye.
Thank you, Mahmoud, for your valuable time and everything.
Okay. Come on, man. Whenever you need anything, hit me up. Thank you. See you guys.